Meeting will come to order. Good morning, ladies and gentlemen. This is the third day in the Science and Committee's series of hearings to investigate the Shuttle Challenger accident. We've had two very productive days so far, and the first with the Honorable William Rogers, Chairman of the President's Commission on the Space Shuttle accident, and the second with the NASA Administrator, the Honorable Jim Fletcher, and Admiral Truly and his staff. And Dr. Fletcher is back today, and we appreciate his joining us again, accompanied by Admiral Richard Truly, Mr. Arnold Aldrich, and joining the NASA group for this hearing is Mr. J.R. Thompson, Vice Chairman of the NASA Task Force. In addition, we will be hearing today from the 6 NASA task teams that supported the Rogers investigation. In addition, we will be hearing today from the 6 NASA task teams that supported. Now, somebody wrote that twice. Now that means we're going to have 12 reports this morning, I think. I believe that our initial progress and pace has been good, and I look forward to continuing our momentum. The committee's task is to conduct an incisive and comprehensive inquiry into the Challenger's crash, using the report of the Rogers Commission as an important basic foundation. Our objective in doing so is to provide for a constructive change in the nation's space operation to ensure its future progress. So again, we want to thank you, Dr. Fletcher and Admiral Truly and Mr. Thompson and Mr. Graham for your excellent, Dr. Graham rather, for your excellent cooperation. Yesterday we've gotten good reports. Members feel comfortable with the progress we're making. And then as we had planned yesterday, our program would be to take and now review in a little more depth from a technical point of view the work that your task force have done in coordination with the Commission to kind of close that gap between our review and your presentation. And then we would continue this afternoon on additional questions and answers and see if we conclude that phase of the work today. So without further ado, I recognize the distinguished gentleman from New Mexico, the Honorable Mr. Manny Lujan.
Thank you, Mr. Chairman. I don't have an opening statement. I'd like to just move right on to the
Very
statements
fine.
and questions.
Dr. Fletcher, we defer to you.
I'd like to defer at this time to Admiral Truly, who will introduce his associates.
Admiral Truly.
Thank you, Mr. Chairman. Shortly after the accident, I recognized very quickly that what was needed was a good organization within the NASA task force, which I briefly mentioned yesterday, and I needed some full-time help from someone who could pull the task force's day-to-day activities together, and quickly came upon Mr. J.R. Thompson to my right here. Mr. Thompson was a former employee at the Marshall Spaceflight Center during the development phase. He was a project manager for the Space Shuttle main engine project and is now at the Plasma Physics Laboratory at Princeton University. J.R. Thompson agreed to come on with the task force full-time, and is just recently, with our conclusion, is now back up at Princeton and is here today to take you through an overview of the technical investigative activities that the task force did in support of the Presidential Commission. So I would like to turn it over directly to him.
Mr. Chairman,
You're going to have to pull those mics. They're not quite as sensitive. We have to be pretty close.
as a way of introduction to today's agenda, I'd like to highlight and summarize the organization that Admiral Truly put together in support of the investigation conducted by the Commission. So if I could have the first chart. With myself and Admiral Truly providing the overview was Bob Crippen from the Johnson Space Center, Colonel Nate Lindsay, Joe Kerwin, and Walt Williams. The NASA task force was structured, as you see on the chart, with 6 teams, 4 of which were direct analogs of teams supporting the Commission. The development production team headed by Jack Lee at Marshall, the pre-launch activities team by Tom Utzman at the Kennedy Space Center, the accident analysis team. I provided the overview leadership for that, but the driving motivator and worker in terms of getting the job done at Marshall was John Thomas. The mission operations team by Tommy Holloway at Johnson, and the search, recovery, and reconstruction team by Colonel Ed O'Connor from the Air Force, and the photo and TV support team by Dan Germany at Johnson that you heard yesterday. Just in terms of the end product of the work that was done by the task force, We delivered to the Commission on April the 18th some 47 volumes of reports. We completed the answer to some 247 action items that were formalized by the Commission. Colonel Ed O'Connor and his recovery team with the Navy and a rather outstanding force recovered some 215,000 pounds of debris, which represents slightly over 25% of the shuttle vehicle. During the course of our support work with the Commission, we conducted some 20 separate individual test rigs, which ended up being over 2,000 tests in terms of analyzing the data and what went wrong during the mission. This was not done just by the task force, including many NASA people throughout the various centers and the contractor personnel. At any one time, there were approximately 6,000 people directly supporting the task force, which was then supporting the Commission. So a lot of people certainly put in a lot of long hours to support this activity. I think we came to the right conclusion. Certainly, the task force embraces the conclusions drawn by the Presidential Commission. And to get into that data, we would like to start with a summary of the timeline. I think you heard from Dan Germany more yesterday on that, but we would like to summarize that, which I believe would be a natural lead in to the accident analysis team. That presentation is going to be given by John Thomas, followed by Jack Lee and the production development team, and then the mission operations team and the pre-launch activities. We will not present a presentation today unless you require from the search team because of your extensive view of that hardware at the Cape. But we stand by to answer any questions that you have in that area and have some backup material if you need it. If there are any questions of me, if not, then we will proceed directly with a summary of the timeline by Dan Germany.
Well, you might want to clarify for the record, if the gentleman would yield for a moment, that as explained yesterday by Dr. Fletcher and Admiral Truly, that this high-level teams of expertise in these particular various assignments worked in coordination between NASA, the agency per se, and under the direction of the Commission, so that the Commission and the Commission's reports, efforts that we have received, is a product of these particular coordinated activities. And that I think we have to get on the record. I want to close that gap. Isn't that what we're doing here?
Yes, sir. Let me speak for the task force. That is very much true. We work very closely with the Commission, answered, to my knowledge, any action that they gave us, and provided them, quite a bit of data.
Dr. Fletcher.
Mr. Chairman, Dr. Graham, of course, was here when this was going on, and I think can clarify the relationship between the task force and the Rogers Commission. He was closer to the Rogers Commission during that.
Dr. Graham.
Yes, Mr. Chairman. When the Presidential Commission was set up, we had discussions with them as to how NASA was going to support their investigation. And it became clear in those discussions early on that they intended to break their activities into a number of subcommittees. This was within the first week of their establishment. At that point, we worked with them to follow the identification of specific subcommittees and specific tasks that they were going to put together. And then when we put together our formal support teams, we mirrored the intentions and the areas that those Presidential Commission task force subcommittees were going to pursue as closely as we could. So we tried to make a structure within our own work which was closely enough a reflection of what the Presidential Commission was going to do that we could have easy and direct channels of communication between each of our groups and the subcommittees of the Presidential Commission. That was reflected in the first four working groups or task force groups that you see on the chart. The other two were then support to the entire operation, and we maintained direct communications across those under the specific arrangements that Admiral Truly set up throughout the investigation.
The work that we're about to review now closes the gap between the expertise and the work that the NASA task force teams did for themselves and for the Commission. There's no gap between those two, no information gap between those two.
There was no information gap, Mr. Chairman. We responded to all requests of the Commission. In addition, when we felt there was an area of investigation or study that needed to be done that the Commission hadn't specifically recommended, we went ahead and pursued it anyway in the technical and accident investigation area. We made the results available to them, and from time to time we suggested to them specific issues or areas that they might wish to pursue. So we attempted to keep as close a coordination between the two activities as we possibly could.
I thank the gentleman. The gentleman from New York.
If I just may, I'd like to ask Admiral Truly a quick question. Was there any limitation placed on the resources that were made available to you for this important assignment?
No, sir.
Thank you.
There were not.
Dr. Thompson, you proceed. I just want for the members, for the record and for the members' information, that we've closed, there's no gap that lies between this testimony and the Commission's testimony. That's the point I want to make. Dr. Thompson, if you could be so kind.
At this point, then, we'd like to proceed directly with the timeline summary by Dan Germany of the Johnson Space Center.
Mr. Germany.
Mr. Chairman and members of the committee, first chart. This is really the second piece of the activities that the photo and TV team worked with during the accident investigation. Yesterday you saw the film that we had. So today I'm going to just briefly run through the timeline that goes along with that particular film that you saw, really for two reasons. One, for the record, and then to provide you some information as you go through your deliberations, and you can help you understand better some of the activities that you'll be seeing from the other teams. Next chart, please. This is a chart of the vehicle coordinate system that we use. And the x-axis is the axis that runs along the vehicle itself. As you can see in the front part of that, anytime you have a roll maneuver, it's about that x-axis. And then the y-axis is the horizontal one that you see there. And anytime you see a pitch maneuver on the vehicle, it's going to be about that particular y-axis. And then the z-axis of the vehicle is the vertical one on the chart there. And anytime you have a yaw maneuver, it's about that particular z-axis. Next chart. Now this timeline, I've got 4 charts that we're going to summarize for you. And let me kind of walk through the graphics of the chart before I get into the details of it. The bar column in the middle is time, and you read it from the bottom of the chart to the top of the chart. So T0 at the bottom is ignition command of the solid rocket motors. It goes all the way up on this chart. We show 22 seconds. And each of the columns you see, starting with the left, the column entitled camera, just gives you an idea of what each of the camera numbers are for which we've pulled the sequences in which you saw yesterday. And then the next column, photographic event, is a verbal description of what we saw from the particular either TV or films. The next column, MET. MET means mission elapsed time, and that's referenced back to the T0 ignition command. We got that on both sides of the vertical bar because on the left side of the chart is photographic activities, and on the right-hand side of the chart is the instrumentation that went along with the particular photography that we saw. Now, this chart is the one that shows the first activities that were anomalous from a photographic point of view that has to deal with the smoke. And at 0.678 seconds there is, you see we confirm smoke, and then we talk about the multiple puffs of smoke that happen. And after that, at 2.7 seconds and 3.3 was the last time we saw the smoke. Next chart.
Would it be profitable for the people that are here, if somebody had a chart and was, or rather a pointer and was just pointing this out as we went along? I think it might be helpful.
Okay.
Because everybody doesn't have the advantage of having a copy of your...
Okay. Crip, would you mind pointing?
You have a pointer?
You got a pointer? Okay. Now, this particular chart
indicates that really nothing was happening in that second period of time from the 3 seconds up to 58 from a
Thompson,
photographic point of view.
Mr. Germany, can I interrupt you again?
Sure.
Let's go back to the first chart and
All
let's
righty.
start over again. I think it's very important because the first phase on the left-hand side where we're talking about the photographic events, you're in effect following in sequence here in chart form what we viewed yesterday by photography.
That is correct, sir.
And it might be well just to reiterate that as we're going along because it gives a sequence that's very important to later on conclusions. If you don't mind doing that over again.
Okay. At 0.678 seconds is where the first time that we saw the smoke. And then from 0.8 up to 2.4 is where we saw the multiple puffs that you saw on the film yesterday. And then at 2.7 seconds was the last time we saw smoke above the right SRB ET attach ring. And what that is telling you is that if it was no longer above it, that means essentially the smoke was not replenishing itself, so the joint was tending to heal itself. So the next point up at 3.3 seconds is when you see the last positive visual indication, and it's below the ET aft dome. So now the vehicle is moving, and you no longer see anything going in the plus X direction, so therefore the joint has essentially healed itself for this particular time period. Okay, next one. Yeah, go to the... no, you're going backwards, Tommy. Go forward. So during this period of time here, from 35 up to 54, we're seeing nothing from an anomalous point of view. Next one, Tommy. Okay, from 58.7 up to 64.7 is where we see the next series of events that occurred. And what's happening in this series is the first evidence of flame occurred at 58.7 seconds. And let me just kind of verbally describe what this chart is going to tell you here. The flame started the first time we saw it, and then it started to flicker a little bit, and as it, from a flickering point, it became continuously and well defined at 59.2 seconds. So that's telling you the flame is progressively getting larger and it's becoming constant. And then later on, at the 60.2 second period, is where it was attaching itself to the ET 2058 ring frame. Now what this is telling you is now the flame is impinging upon the ET, and from this point on is when you're going to start to do the damage to the external tank itself. The result of that is shown at 64.6 seconds. Crip, if you could, right there, is the first indication of the leak at the 2058 ring frame. So this is telling you now that the external tank is beginning to leak as a result of the impingement of the flame upon the tank. Okay, next chart please. So the leak has started now, and we didn't really see anything else from an anomalous point of view from that point until we get to the 73.1 second point. And that is the LH2 tank failure. When the LH2 tank failed, and if you look at the right-hand side of the chart, Crip, at 72.2, start the divergent yaw rates. The R means right and the L means left here. The difference between the right-hand booster and the left-hand booster. Now the right-hand booster is starting to move away as it broke off, and you remember the CAD picture yesterday when we saw it rotating like that? So the booster is breaking away. The LH2 tank has failed. Now here's what's happening. When that LH2 tank fails, you have a large, the hydrogen itself is coming out of the bottom of the tank. You get a little bit of a extra thrust rippling up through that structure. The right-hand SRB is starting to move, and it crunches into the inner tank area, as you saw yesterday. And when that happens, you lose the structural integrity of the external tank. And when that occurs, then there's nothing to hold the vehicle together, essentially, because it's all tied together through the external tank. So from that point on is when we get the structural breakup occurred, which we call the point at 73.3 seconds greatly increased intensity of the white flash. This is where we feel the structural breakup occurred. And I believe that's the last of the charts. And that's just a brief summary for you, Mr. Chairman. Are there any questions?
Are there any members that have a specific question on this first phase?
Mr. Chairman.
Wait a minute, let me see now. Mr. Walker from Pennsylvania.
First of all, Mr. Chairman, I do have a statement here I'd like unanimous consent to put in the record.
No objections, so ordered.
Thank you, Mr.
Want
Chairman.
to turn those lights on for the moment?
There is that long period of time between, or a fairly substantial period of time, between the first puff of smoke and then the visible flame. Do we have a theory about what happened there? You said the joint appeared to heal itself. Do we have a theory about what that process was of the healing, and then what ruptured the joint again at approximately the 62-second point?
Ms. Walker, let me do this for you. I'm going to give you a little bit of an answer, and then Mr. Thomas, who's going to be following me on the accident analysis team, will go into it in more detail. But since you ask it now, I'll give you part of the answer right now. As the smoke occurred and the erosion started of the O-rings, we believe that what happened, a combination of the exhaust products tended to, in the vehicle dynamics, stop the twang in the vibrations after that first 3 seconds. It tended then to seal. Then as it went later into flight, you go through the max Q region, which is maximum dynamics pressure, the vehicle starts the isolation and the vibration again.
When does that start?
Well, max Q occurred, let me just, so I won't have to guess the exact answer for you. Max Q occurred at 59 seconds.
59.
Maximum dynamic pressure. After that point, then we feel the erosion began again, and that accounts for that. Now, Mr. Thomas will go into more details for you if that satisfies you right now.
Thank you, Mr. Chairman.
Further questions? The gentleman from California.
Chairman, I think we've understood that the crew had no way, nor did ground control have any way of knowing the progress of this 73 seconds in terms of the anomalies. That's correct, isn't it?
Yes, sir, that is
There was
correct.
no monitoring systems that would have alerted them to the progress. At what point in time well, apparently there was no point in time where they could have shut down the motors
No, sir.
and stopped the process of going, even had they known.
That's correct.
They would have either had to abort it and cut the shuttle away from the rest of the hardware had they known, but that would have been the only thing they could have done. No way to have salvaged the mission.
That's correct. We didn't have anything at all that would allow them to correct the situation or to leave the situation.
Thank you.
Mr. Barton, I'm sorry.
Thank you. I just have two quick questions. Number one, based on what you just said, how close, in spite of all the screw-ups, did the mission come to not disintegrating? And number two, if it wasn't, were there some unusual wind shears that caused excessive, I think you call it maximum Q, that if it had been a normal wind situation, that wouldn't have occurred? Does that make sense to you?
Well, I'm not sure if all the questions directly, but
I mean, it appears that there was a chance, in spite of the cold temperature, the ring did seal, and for a certain amount of time, everything was working okay.
The gentleman would yield. I think it would be more profitable. We've only seen the first blush. We're going to have an analysis presented by the accident analysis team, and it might be better if we listen to what their analysis is, because the questions that we're generating now relate to that issue. If that's satisfactory to the members, I think it'd be more profitable, and we'd at least have the full background before us. Is that all right? So why don't the gentleman hold on his question?
I would like an answer to the first question.
I didn't. All right.
If they feel that the mission came close to being successful in spite of all the problems.
No, let me try. The answer is no. We don't know how the leak would have continued to grow had the vehicle not broken up where it did. But I know of no analysis that said that we would have could have sustained that leak that was growing at an unknown rate until separation, and the axial thrust caused by the exhaust at the time of separation would have also created an unknown separation condition at the time of solid rocket motor separation. So the task force never was able to develop any conclusive data that would have shown that the mission could have been a success. You could postulate that, but we had no data.
All right. Under those circumstances, I believe is your next plan to have the accident analysis team's observation presented by Mr. Thompson?
Yes, sir.
Next. Suppose we proceed with that.
Use a mic, Jan.
Okay, John. At the time of the accident, Mr. Chairman, John Thomas was the manager of the Space Lab program at Marshall. Then he was instrumental in providing the leadership for this accident analysis team. And with the conclusion of our work, he is now leading the redesign activity on this joint on a solid rocket booster.
Mr. Thomas.
Thank you, Mr. Chairman.
We'll have to pull those microphones closer because we're having difficulty hearing, and it's not your fault, it's the microphone's fault.
Yes.
We're hoping NASA will design a new one for us in due course along the line.
Okay. Could I have the first chart, please?
Right.
Mr. Chairman and members of the committee, I'd like to discuss with you today our activities within the task force dealing with the topic of accident analysis. Next chart, please. And to set the stage for doing that, I would like to describe for you the approach utilized in the accident analysis process. It was structured from the very beginning, observing the incident, obtaining the flight data, the photovisual coverage, and the observations from the flight. From that, we developed a fault tree, and that fault tree was constructed using the data from the incident, the anomalies that we did observe early on, the observable vehicle failures, that is the explosion, and all the failure sources that could produce such
Well, the gentleman, please suspend. We have a call of the House. We'll have to go. I don't want to lose the continuity because your testimony is too important, and I want to keep it in continuity. So we will have to recess for 10 minutes and vote. And if everybody would please come back right away, because soon, in 10 minutes' time, we're going to proceed to go through this program in depth.
Yes.
All right. We've got to get a little closer. These guys can't do it.
I forgot. You know, I've got this factor, and then we have the companion that says, hey, that even though we did everything right on the right joint, you still can have some joint sealing degradation. I forgot to put that in.
There's nothing wrong with it.
This one's good. The next one, my second finding in the report, was the one that we put in, remember, that said that even though you put the SRB joint together, there can be degradation. We just flat left it out.
That's fine. Don't.
Well, what I thought I would do.
I mean, somebody's going to detect it. Well, you can add the words to it.
That's what I would propose doing. I'm going to say, even though I omitted this, I would like to say that.
Okay, we will.
Again, the committee will reconvene. We were just about to begin with the presentation by Mr. Thomas. If you'd be so kind to begin again, sir.
Thank you.
Mr. Thomas. I beg your pardon.
It should be noted that our senior astronaut lost his position to an electronic pointer.
Where is
he was
it?
pointing out on the charts for the presenters. Now he's lost out to an electronic pointer. That just goes to show the advance of technology.
All right. I missed that. Okay, are we ready?
Mr. Chairman, I was in the process of defining the analysis approach that we implemented in the accident analysis team, beginning with the incident, and from the incident developing a fault tree that included the anomalies, the vehicle failures, and the source of those failures. And that was for each and every element that was aboard the 51L flight. Having defined the fault tree and the potential sources for cause of the failure, then we developed an incident database, or an accident database, consisting of a large amount of design and qualification data, the assembly test, or assembly and build test and checkout data, determined the flight environments, the data that was received from the flight on the downlink, and other data from the ground, the various tests and analysis that had been conducted and would be conducted in the future in a closed-loop fashion, as well as the recovered hardware and a detailed listing of anomalies that had been experienced in the past. Having this database, then we reviewed the database and developed from that a number of scenarios that would have led to structural breakup of the vehicle. We postulated the sequence of these scenarios and then evaluated their credibility. And in evaluating that credibility, it required that we do additional testing and analyses, which is also shown in the process, where we had special test setups, special analytical models developed, as well as those that were existing at the time. And then we took the results of those, fed those back into the database, and then cycled back through the scenarios. Having then an iterative process of testing credibility of each one of the scenarios, finally winding up with conclusions of what we suspected to be the causes and the findings of the accident analysis panel. Next chart, please. Then to carry out this process, we established an organization that is listed under JR and myself in the top block. We established a group for each of the major elements, that is the shuttle main engine, the external tank, the solid rocket motor, one for the solid rocket booster, and for those things that transgressed across all of those systems, a systems working group. We also treated the payload, which was an inertial upper stage and the TDRS satellite. We then had recovery support involvement down at KSC, and we kept very close with that. The photo analysis support was very important in this process in determining events and the times of those events that supplemented the downlink instrumentation. In addition, the orbiter was thoroughly reviewed. The installation process, as well as the analytical process leading to payload installation into the orbiter, was reviewed, and the Goddard Space Flight Center reviewed the TDRS and the other payload aboard 51L, the Spartan. That is the major payloads that were in the bay. This group met, could I have the next chart, please? This group met continuously, were in session continuously, from the time of the accident. There were pre-established contingency plans in place for each one of these groups. They were implemented with, particularly for the major elements, within hours following the accident, and were in session up even prior to the formation of the task force, and then we carried forth with those. Task force was established in early March, and from that point forward, you can tell in the middle of the chart there those areas where we met with the commission, and preceding each commission meeting, we had a very rigorous session with our counterparts on the commission called the Accident Analysis Panel. The other major milestone within this scenario of events is the 18th of April, and that's the time that the report was prepared and submitted. Could I have the next chart, please? Now, proceeding into the analysis itself and the findings, first I would like to give you some very summary level findings, and then from there I will progress to describe each one of the findings and later on determine or show to you the determination of the various failure mechanisms that cause the seal to leak. The first finding, of course, is that the right-hand aft field joint leaked hot combustion gas, and that was from the solid rocket motor, of course. And in the second event, as Mr. Germany pointed out earlier, was that leak contacted the external tank and weakened or penetrated the hydrogen tank. The hydrogen tank then was breached by this penetration or weakening, and it then initiated the process that led to the structural breakup of the total stack. And that also in these findings we determined that there was no other element of the STS or its payload which contributed to the cause of the accident. Now, if I could take those then one at a time and begin with the solid rocket motor description on the right-hand chart, you will see the solid rocket motor up at the top. It is assembled at the factory in casting segments, which there are 4. You see the forward segment and then aft, and those segments at the factory have what are called factory joints, and they are covered over with insulation and propellant as delivered to the launch site. At the launch site, the solid rocket motor is assembled using these 4 segments, and at as each segment is joined, there is a field joint, and the field joint I've shown by arrows emanating from each of the 3 that shows a cross-section of the field joint down below that. May
I interrupt you and ask a question there?
Yes, sir.
Is the configuration and the structure of the factory joint the same material makeup other than the sealing insulation on the outside as would be the field joint?
Yes, sir.
In other words, it's still a no-ring type of configuration, but it's sealed in the factory?
Yes, sir.
Thank you.
On the left screen, I've shown a colored cutaway of the field joint, and if I could start on the right-hand side of that, is the propellant in the red, the insulation in blue, and there is a liner that is shown in gray there. The brown between the insulation is vacuum putty, and the metal parts then are shown, the clevis, which is in orange, and the case tang, which is in purple, and the O-rings that seal those 2 metal parts are in green. The joint is pinned together by around a given joint by 177 pins that are shown in this schematic in yellow. Those pins are held in place by a metal band that goes around the circumference of the total vehicle, holding those pins in place, and that is covered over with cork that is shown in green. You can see the leak check port also in a lighter brown that is utilized to leak check the 2 O-rings. This joint configuration is the one that failed, and the failure mode was that the gas came through our analysis is that the gas came through the putty between the insulation, the O-rings leaked, the gas then either went down around the tang in this direction, down here and out, and as the metal heated up, the penetration exited, or the hot gas exited here, the hole then became larger, or as the gas came down and out, this area right here in the tank was overheated, and the emanation of the hole was at that point. In any event, the hole, which I will describe to you shortly, began at this joint. Have the next chart, please. This is a photograph of the recovered hardware that from this particular right-hand aft field joint, and the photograph is taken looking from this direction from inside out. It is the top part here, represented by this schematic. This is the hole here, and that is what one can view here. These are the pinholes, as you can see, those pins right there, on this side and along the bottom here. The white is the insulation. This black is the propellant as it has burned forward, and this is the actual melted metal. This is approximately at the 300 degree position on the spacecraft. Next, please. This is the lower half of this joint, that is this part, depicted schematically here. This is the hole that goes from this point to this point, and that's approximately 33 inches. Again, the propellant, the insulation, and the metal. There is a secondary hole in the metal at this point that we believe occurred or penetrated very late, in fact, after the 73-second time period, due predominantly to recirculation around the external tank attach ring on the outside. It was, we feel, from outside to inside burn through. Have the next charts, please. On the left is a sketch of the vehicle looking forward with the right-hand solid rocket motor here, and the leak that I was just talking about from a circumferential standpoint occurred at this point right here, then contacted the external tank in this radial location, and from then forward the dome then exited the external tank. And that longitudinally is right there where I have the arrow pointed, slightly around on the other side of that solid rocket motor. Next, please. I mentioned that we had prepared a fault tree earlier, and I have shown that at a very summary level on these two charts that are on the screen now. If I could just briefly explain the two screens. This one is the total summary fault tree. As you can see, it has the orbiter, the main engine, the payload, the external tank, and the solid rocket motor. This chart on the right screen takes these two elements of the fault tree and gives you an indication of the next tier or next level of detail that was postulated that could have caused the failure. The color code with respect to understanding the chart is the green represents an improbable cause, the red a probable cause, and the yellow a possible cause. In this fault tree, we started, in fact, as you start and go backwards in development of a tree and test it then in the opposite direction. We started with the total breakup, we observed the external tank breakup, and then we postulated those things that could have caused that, the orbiter and so forth. Then the next level down would be to determine what within, for example, the external tank could have produced that observation there. And that was damage at liftoff, premature That is the range safety system called a linear shaped charge. Destruction, a structural flaw, or an overload could have caused structural breakup of the tank. And in fact, we cleared all those as not being the cause of this accident. Then one would move down to the solid rocket booster and again consider loads, consider that the integrity of the pressure vessel was violated, and it also has a range safety system aboard, and we determined that it was not at fault. The red then, the way one would follow this logically is from here to here to here, and then back down, and then you get finally down to the point that we have a joint seal anomaly. The conclusion is then that there were no other contributors to the accident other than the solid rocket motor. And the solid rocket motor joint leakage. Now what would then cause the joint to leak? And these are the factors that we determined to contribute to that leak. That is the gap opening due to joint dynamics, and I'm going to go into these a little bit further. But this first one, the dynamics, the joint temperature at launch affecting both the resiliency of the O-ring and the potential for ice in the joint damage and or contamination during the assembly process, O-ring squeeze after mating, that is, has been referred to as also as static O-ring compression, putty performance, which is a pressure holding capability and also referred as pressure actuation time, assembly blowholes, which can produce O-ring erosion. I'd like to take each one of those individually and describe it for you. Next chart, please. The gap that I have reference to when I say that the gap opening is, as shown right here, at the upper left-hand corner of this screen. This is a cutaway of the joint in the static condition. The joint is in this configuration, relatively straight from tang to clevis. And the O-rings are located in here, and the gap is the gap between this land between the O-rings and this tang. As the motor pressurizes, the ends of the clevis and the end of the tang tend to bow in this direction, and this is the internal pressure, of course, is on the left side of the tang and clevis. This bows out, and you put a bending moment in the clevis, which causes the tang to move away from this inner clevis leg at this point, therefore opening up the O-ring gap. That is what has been referred to as gap opening and also rotation of the joint. Depicted also on the curves, the abscissa here is time in thousandths of a second, and this is the gap opening at these points right here for the primary O-ring, which is located in this slot, and the secondary O-ring located in this slot. And as you can see, as the motor pressure builds up with time, these gaps begin to open and open at a fast rate between 200 and 300 milliseconds after ignition, and finally wind up with the primary O-ring gap opening as much as 27 to 29 thousandths, and the secondary opening on the order of 15 to 17 thousandths. And we believe that these, in fact, have a probable influence in the cause of the accident.
Mr. Chairman, could I ask a question?
The gentleman's recognized.
Is that the normal performance of those O-rings, or was that the performance during the accident?
I'm particularly describing the metallic part of the joint at this time, and it is normal. The O-rings in this case, which I would talk about a little bit later, in in theory and in design, should track that opening.
Okay, but that is a normal occurrence in the flight right there.
That is.
Mr. Chairman, I have a quick question.
Gentlemen.
Is the maximum pressure time, pressure from inside the tank, is that concurrent with the maximum turbulence time?
No, sir. The
About the same-
maximum pressure is immediately at the right after ignition, and it drops downward as you go toward the area or the regime of maximum dynamic pressure. Once through that, it builds back up slightly.
Okay, thank you.
The gentleman proceed.
It should be noted also that that this aft joint is the aft joint on both sides of the vehicle is in fact opens less than those that are forward, and that is normal as well. But we do conclude that this is a cause, potential cause, in combination with the other effects for the accident. If I could have the next, please. Joint temperature is a factor that must be considered. Tests show that the O-ring resiliency significantly decreases at the temperatures experienced on STS-51L. The cold O-ring would not track the gap opening rate without pressure assist. And what I mean by that is that the pressure assist is pressure from the motor getting in the O-ring groove and forcing it to a closed position. That there must be room in that in the O-ring groove for the pressure to enter that groove and provide the pressure assist. On the right-hand chart, I have shown the temperatures for the two lower joints, the aft field joints for both vehicles, or both SRBs, the right and the left. The little insert up at the top shows the radial clocking on the right-hand solid rocket booster, the left, and as you can see, the right-hand solid rocket booster temperature around the periphery varied in the way that is shown here from about 30 degrees at that position. It built up as we go around to between the 90 and the 180 degree and then drop back down. The reason for this is that this is at time of launch, but at the time of launch the sun angle was about from this direction, which put the sun on this side of this solid rocket motor. On the other side it was shielded on the left-hand side, and as you can see, that was a relatively steady temperature on the order of 30 degrees plus or minus 2 or 3 degrees. Analysis and tests indicated also that at these temperatures that ice could be in the joint, and that would be formed from water that penetrated the joint during a rainstorm or inclement weather while the vehicle was on the pad. And we did show that by analysis that ice could be at that location within the joint, and further tests showed that if ice was there and should it freeze, it will unseat the secondary O-ring. I think it is needed to be pointed out that most all of the 51L joints up the vehicle tended to follow this same temperature distribution pattern around the vehicle, although they would be slightly warmer. So we conclude from this that the joint temperature is a probable contributor to the cause in conjunction with other factors. Next, please. During the assembly process, with the tight tolerances that we must maintain, there is the potential for some damage to the O-ring or the metal, or there is the potential to create contamination that could affect the sealing performance. And with respect to tightness of the tolerances at the locations that would be experienced during the 51L, I've shown each one of the joints as they appear on the stack. The top one is the right-hand motor. The lower is the left. Again, with the clocking, this location here on the right hand, as I've shown with this arrow, is the location where one would expect either at this location or the one 180 degrees opposite, are the locations that one would expect damage during the assembly process if it occurred, because this is the location of the maximum ovality as measured during the mating process between the two segments. You can see that this one is the worst. The others are less than that as you look around the other 5 joints. Even with this process, we looked to see if there had been metal-to-metal interference, and analytically, it would appear that there is no potential for overstressing the components should that have existed. We also showed that by some subsystem testing, subscale testing, that contamination could be produced at that joint, but we had to work at it a great deal in order to produce that contamination. We have had some very, very limited experience of O-ring damage in ground tests. However, we believe that to be associated with the ground test assembly process and not necessarily directly applicable to the flight motor. But in any event, it was possible to have created the contamination or damage, but we believe that with the care that was taken and with the dimensions that we actually measured, that it was improbable that contamination contributed to the 51L accident. Next, please. A very important factor to be considered, particularly in conjunction with cold O-rings and their resiliency, is the squeeze, that is the degree of compression of the O-ring around the joint. It should be noted also that at this location where I pointed a minute ago that the maximum potential for damage could occur, this is also the maximum point of squeeze on the solid rock, on the aft field joint for the right-hand motor. And that is also the point where we observe the leak. It's around the 300 degree position around the vehicle. So we find that these conditions with this maximum dimensions could produce max squeeze on the O-ring. Now, if one puts max squeeze on the O-ring, this then reduces the pressurizing volume that it might have within its groove. And as we have shown by subsystem testing, that with an initial gap between the O-rings and the tang of 20 thousandths, which was considered to be the nominal prior to 51L, it would seal down to 10 degrees. And I guess I should stop now and explain my color code. The green is that the test that we performed would pass. The yellow was that we would have some leakage, but it would finally seal. And the red indicates that the joint would not seal at all. Down the left-hand side are the temperature ranges for which we tested. Across the top are the pressure reaching the O-ring at ignition, at the time of ignition, and the right-hand column is that the pressure is delayed some 200 milliseconds to 500 milliseconds, which which is associated with putty that is the next topic. This is the squeeze of 4/1000ths on the O-ring. This is a nominal squeeze of 20, and if we can direct our attention to these two columns right here, it would show that with a 20-degree or 20/1000ths initial gap, that the joint would seal down to 25 degrees, and there would be then the potential for some leakage, but it's sealed down to into this area, but it would not pass when we tested lower than 0 degrees. With an initial gap of 4/1000ths, if I could skip one line for a second, 4/1000ths, which is maximum squeeze, it showed that the joint, high confidence sealing of the joint was only down to about a temperature of 55 degrees. In this 40 to 50 degree region, there was a question of whether it would finally seal, and then below 40 degrees it was shown that by these subscale tests that it would not. Now, these subscale tests are not finite in their discrimination, but they do give one enough information to describe the relative thresholds at which passing or failing would take place. In order to test the squeeze theory, that is that the tighter the squeeze, the higher the operating temperature must be, we installed some tests which I do not have shown on the right-hand chart, but showing that with a 10/1000ths gap that it would seal down to 25 degrees, which says that the threshold is somewhere on the squeeze from 4 to 10/1000ths of an inch. There is one other implicate.
Gentlemen?
Might I ask when that squeeze test data was obtained?
The gentleman's asking, when was the squeeze test data obtained?
This particular data was obtained post-51L accident. It was during the investigation process.
So you have nothing to compare it to prior to the investigation?
No, sir, we do not. There.
Could I ask a question?
Gentlelady from Kansas, he's almost finished, but the gentlelady from Kansas, go ahead.
Well, in previous damage to the O-ring, because it had shown up in previous flights, had you been able to identify what was causing the trouble? Was it a squeeze or a burn or?
Earlier in those that you have reference to, I think it's the erosions and blow-by earlier in the program before 51L.
Yes.
Those were attributed to, in every case, to a blowhole where the O-ring was eroded, to a blowhole in the putty that allowed a hot gas jet impingement, or hot gas jet to impinge upon the O-ring and erode it.
Right. So that when you talk about the squeeze problem, that is a result of the cold temperatures?
No. The squeeze per se is a result of the dimensions of the two mating motor cases and the mating process, how they come together.
I understand that, but you had said that the squeeze was not a factor previously, and so did that have something to do with the cold temperature?
When I answered the previous question, I did not intend to mean that it was not a factor previously, that it was not known to be a factor previously, okay, prior to 51L.
Well, if the gentlelady would yield now, I want to finish this, because we're losing continuity. I want to finish this continuity, and then we'll have ample time to get into depth, because I see here that there's a series of questions that should emerge here, and the gentlelady is right on target, but I'd rather wait and put them into context, otherwise we're going to be all over the lot, and we're going to lose the context that I'm trying to create for the record. So if you please bear with me, the gentleman would conclude. Mr. Thomas.
Thank you. There is one other factor in this O-ring squeeze scenario that surfaced during the investigation, and that is that the cases, the case walls and diameters appear to grow slightly on the order of, say, 20 to 30 thousandths after 4 to 5 uses. This was determined during the investigation process, and that must be reckoned with for the future. The maximum squeeze is considered a probable cause in conjunction with other factors. Next, please. The last factor is that is considered to be in the probable category is putty performance, and tests showed that the potential for putty to delay O-ring pressurization during the ignition process. However, that is performance is variable. Sometimes it will delay the pressurization, and sometimes it would hold. A hole would become in the putty and it would pressurize immediately. This was further substantiated by the presence of blowholes in the putty prior to 51L in 16 of 138 joints. We also determined during the investigation and the destacking of STS-61G, which was a vehicle that was stacked after 51L. It was found that several of the joints in the 61G contained blowholes, which would have occurred during the assembly process, of course. Tests confirmed that delayed pressure actuation could result in failure of the seal. If it holds the pressure off by 250 milliseconds to 500 milliseconds, the joint would fail at the max squeeze conditions and at the low temperatures. And that's shown in the right-hand column of the chart on the right. Again, the green is pass. If we have maximum squeeze at 55 degrees, we delay the pressure 250 to 500 milliseconds. Then it will with 4,000 squeeze, it will pass down to 55 degrees and down to about 40 degrees with nominal initial gap opening, but lower than that, the seal would not pass. So putty performance is a variable, and it is considered in the probable category. The last slide, please. We could not determine that any single causing mechanisms, that is, those that we just discussed, could be discerned. The damage and contamination at mating we believe to be improbable, but it takes a combination of others to form the most probable cause of the 51L accident, and those are the gap opening, the O-ring squeeze, the low temperature, either involving O-ring redundancy or resiliency or ice in the joint, and the variability of putty. And the conclusion was that the joint must be redesigned to eliminate the effects of these conditions. And that is all I have, Mr. Chairman.
I want to thank the gentleman for an excellent in-depth presentation. I think that we're again have to vote regrettably. Is the gentlelady from Kansas still here, Ms. Myers? What we'll do is to, because you are developing a good point, what we will do is to recess, again, so we can keep continuity going, recess for 10 minutes, we'll vote and return immediately, and then the chair will defer to Ms. Myers to continue that process she was on in reference to the pressurization. So you'll be up first when we return. So we'll recess for 10 minutes.
Yeah.
You didn't pass out your little show and tell. This mic is directional, such that when you talk at it like that, it doesn't work. I don't know what to do. Poor mics. Almost like feeding
Get the letter?
No, I didn't. I really.
Oh, that's no problem. No, it's good. He was something I ought to be able to deal with. You got a lot of trauma, that's fine. No, you can deal with it. You may not agree with all. John's got the data, but both of these on the, here the two halves of the joint that fail, both have been used before. And as I recall, it's either 2 and 3 or 2 and 4. We can get the number, but it's like 1 and 2. We're trying to figure out
Committee will reconvene. Members, I'm sure, are delayed, unfortunately, on the floor, but we're going to go on. What I would like to do at this point, in view of Mr. Thomas's presentation, I think that there's been considerable questioning that has emerged, as you know, over the last 3 or 4 days since we've begun the hearings, in the specific area of this specific area of which we're discussing. And I think it would be profitable for us to review 4 or 5 of the elements that people have on their mind and be done with this part of the issue, which is really what happened in the accident per se, and vis-a-vis the relationship of the O-ring plus other temperatures in the other areas that we have been discussing. I know we have other representatives that have further testimony to give Dr. Thompson, but we'll take that up as we go along today. Now, having said that, for the record, I would like to ask this question just to get it into the record for anyone who chooses to answer it. Maybe Dr. Fletcher, you might want to direct one of your folks. During the course of the photography that we reviewed yesterday, at the 0.678 seconds, the black smoke was observed. And there were 7 or so puffs that followed, caused by, and then the question is, the burning of material. And now for the record, what material do you believe was burning at the time?
Mr. Chairman, we believe that that material that was burning was the insulation that is shown as NBR on that joint photograph, and the grease, and possibly the O-ring to some extent.
The question that follows on that answer, and that's the answer that comes from the Commission's report, given that the insulation is designed to protect the casing, how could it burn?
The insulation was eroding, and by eroding it burns down a little bit and flakes off, and burns down and flakes off, and in that process it releases heat and provides the insulation.
The final question to this, for the record, that given the small volumes of the O-rings and the grease per se, how could so much smoke be produced quantitatively?
I speculate, Mr. Chairman, that was the NBR, and there are ample amounts of NBR, the insulation.
The insulation, all right. Now, in the course of the testimony we've had, starting with Dr. Thompson, then yourself, Mr. Thomas, filling in, there was the areas that were covered fundamentally, which I want to concentrate on, was the joint situation, the weather situation, the putty situation, and in effect, I wrote down to myself the torque situation, meaning the change of pressure because of the dynamics of the vehicle itself on the O-ring, okay? Those are the areas that people now are beginning to want to get into in more depth so that we can lay to rest once and for all any doubts or questions and answer any questions, hopefully, that these folks may want to ask at this point to get upon the record. Is that, you understand where I'm coming from on that? Now, the lady is not back. Therefore, I will defer to the ranking minority member, Mr. Lujan from New Mexico.
Thank you very much, and thank you. Mr. Thomas, there's one saying that in all the readings and studying that comes to mind as to something that might have happened, and I haven't heard anyone talk about it yet. My understanding is that when you begin to stack everything together, you first stand the solid rocket boosters up, pointing up. Then you add to that the external tank, and then you add the shuttle onto that. Is that correct, the way that it's all put together? I further understand that after the external tank is put on, it is then filled with the fuel. Is that correct?
Yes.
And that at the time that it is filled with the fuel, it is already attached to the solid rocket booster. When it is filled, when the external tank is filled, the coldness of the fuel makes the external tank contract. And my understanding is that it's 4 inches that it contracts. When it does that, of course, it's got to pull away from the solid rocket boosters 2 inches on each side, assuming that it's all equal. Could that contribute, because the damage was near the struts that hold the external tank and the booster together, could that pulling away those 4 inches by contracting the external tank have contributed to the weakening in that general area? Was that studied in the entire process that you went through?
Yes, sir. We revisited all of the stacking loads as the vehicle was assembled to determine if there was anything in the process that caused us to exceed our design allowable limits. And that the stack configuration as it sat on the pad with the propellants loaded was analyzed. And it was determined that there were no unexpected or unusual loads produced prior to the 51L liftoff.
Well, but we've had the damage at that joint all the way along. My question is there a spring or something? If you're going to move 4 inches, something's going to give somewhere where that strut is attached on both sides. Whether that could be a contributing factor to the other 13 times that there was damage inside the joint.
I don't recall specifically what the shrinkage circumference or radially of the tank is there, nor what it is longitudinally, but in the longitudinal direction is where it shrinks the most. That is, it gets shorter. And that is taken, the deflection there is taken into account by having the strut slightly at an angle such that when it does shrink, they're up at the proper horizontal angle. And the preloading in the struts is accounted for in this shrinkage calculation, both radially and longitudinally. I just don't happen to recall the numbers, sir.
The struts aren't rigid? Or
the struts are hinged at each end.
At each end. So that the up and down would be compensated for with those hinges. But, well, I'm not sure now whether it's 4 inches that it shrinks in circumference or not. My understanding was 4 inches. Now, it may be from top to bottom rather than...
I would be happy to provide that for the record, sir.
Thank you, Mr. Chairman.
I thank the gentleman from Mexico. May I ask for just a clarification again for the record? As I understand it, when the O-ring was originally, the joint and O-ring system was originally designed, that the understanding from an engineering point of view is that upon launching of the vehicle, that the torque or the pressures that were put up, I would say torque at that point, literally helped to seal the O-rings. Wasn't that the original conception?
That is my
In
understanding,
the
sir.
earlier original design? That was what I think we heard testimony to. And then it was determined after a point in space, you'll pardon the euphemism, in a point in time, it was then determined that instead of that occurring, that those pressures that evolved during the course of launching literally pulled away from the O-ring and worked the opposite. Do you recall that discussion?
Yes, sir.
When was that latter phenomenon discovered?
I don't remember the chronological time, but it was around the time that the structural test article was tested at Marshall.
It's the hydro booster.
It's in the late 70s, I believe.
And that's what I'm trying to get at. So it was determined from an engineering design point of view in a given time and space in 1977 or whatever, that instead of the joint and the pressure on those O-rings working X way, it was just the opposite during the launch because of countervening pressures, and it worked the opposite way. Is that a factual
That's
statement?
my understanding, sir.
Okay. I think that's important to keep in mind. Chair recognizes the gentlelady from Kansas, Ms. Myers.
Thank you, Mr. Chairman. Several of us up here, I think, were confused about the O-ring squeeze, and I thought that when the two parts were put together, that it was actually opened wider so that then the O-ring would not fill the gap and prevent the gases from going through. And that's why I was asking the question about whether the cold weather was involved and whether it had ever been involved before or showed that kind of damage before.
Regarding your first understanding there, as the two halves are mated, the squeeze on the O-ring around the circumference of the sealing surface will vary, but not to the point that it would create a gap between the O-ring and the sealing surface. It is just a differential amount of squeeze as you go around the vehicle on the O-ring. So from that standpoint, it's not a problem during the stacking process. What turns out to be a problem is that if you have maximum squeeze on the O-ring, that is maximum compression, in conjunction with cold temperatures, that is when the O-ring performance or the joint performance to seal degrades, because the fundamental problem with that is that you cannot get pressure behind the O-ring to actuate it to seal, and the cold weather has prevented it from being resilient enough within itself to follow the opening of the gap as it rotates or as it opens during motor ignition.
Okay. Was the putty part of the original design, or was that something that was added later to protect the O-ring?
It was in the original design for that purpose.
As I understand it, Mr. Chairman, there was a briefing last October at NASA headquarters in Washington about the O-ring problem. And Morton Thiokol briefed people in Washington about the O-ring problem. Who was at that briefing?
You're asking people that weren't at headquarters at the time. We may have to supply that for the record unless somebody in the back row, can you?
I believe Mike Weeks was a senior man at that meeting, and Mike is here today. Is he?
Well,
Mike Weeks is here, Mr.
well, I mean,
Chairman.
that's a statement of fact. Would you provide for the record who was at that meeting? I think that'll be adequate.
Yes, sir.
I'm trying to stick to the technical questions now so we don't lose the continuity. Okay?
Thank
We'll
you.
bring
Chairman,
that up.
I think that is a very important question, though.
Well,
about who was at the meeting and what they were told.
if the gentleman would yield, there are a plethora of important questions just to be asked. What the chair is attempting to do at this particular session, while we have the expertise that are here, is to take and establish a series of factual events as to the issues involved. We will expand. We got all afternoon and days to expand on that. But we have these technicians who have been flown in from all over the country. I don't want to lose the value of those technicians' knowledge while we're asking questions that are germane, but I want to deal with this issue today so members thoroughly understand the technical issues so we don't have to go back and revisit it 500 times. And then we're going to get more work done. That's
Could I
where
ask one more technical question?
Yes, of course you can.
I think it was indicated in the report that the putty may have been dislodged or may not have stayed in place because of the testing once the rocket was put together. Is that accurate?
After the segments are mated and they have the putty in between the joints, and there is a leak check of the O-rings that is performed using the leak check port between the O-rings, which is pressurized to 2 pressure levels. An initial pressure is induced into this small cavity between the O-rings of approximately 200 pounds per square inch. That is to seat the O-ring. It is dropped back down to 50 psi and locked up and monitored to see if there is a loss of that pressure indicating an O-ring leakage. There was the postulation that this high pressure, the 200 psi, may have blown by the O-ring before it seated and then have been trapped by the putty and then continue to blow through the putty, creating a blowhole prior to ignition. And we have not been able to determine whether that is fact or not. It was only a postulation.
Thank you.
Would the gentlelady yield on that point?
Yes.
Thank you. My understanding was that as the O-ring sealing problem became more and more increasingly apparent, that the pressurization levels were increased as kind of a fail-safe check on the seals. And then as you increased up to 200 pounds an inch, as a pre-flight readiness and inspection, you may have potentially negatively affected the putty variability. Am I correct?
That is what the statistics show.
So you had a counterproductive safety program, as it were. The safer you tried to make it by that means, the more likely the accident, if we understand the problem correctly.
Well, I think it's important to note that the higher the pressure, the more the incident of O-ring distress, but it did not appear to make that distress on an individual O-ring, to my recollection, worse.
Chair recognizes the gentleman from New York, Mr. Scheuer.
Thank you, Mr. Chairman. This pretty well does explain,
Mr. Thomas, according to the Rogers report, and I quote, "Prior to the accident, neither NASA nor Thiaco fully understood the mechanism by which the joint sealing action took place. We know there were a number of early warning signals from 1983, 2 different warnings in 1985, up to NASA headquarters. So they had an impressive body of evidence there that things had gone awry and that there was a very real problem that needed to be addressed. Now, I'm impressed by the report that you have assembled in the short 6 weeks since the tragic Challenger accident. I'm very impressed by the enormous database that we now have about the O-rings, the faulty O-rings, and the field joint behavior. I'd like to know, how much did it cost to accrue this information since Challenger? How much personnel did NASA assign to that? And above all, for goodness sake, why wasn't this work done after repeated early warning signals that that emanated from Marshall, but did go up to NASA Central Headquarters on at least 3 occasions, as outlined in the report, so that they were alerted, they should have known. My question is, why wasn't the remarkably fine work that you and others have done in the last 6 weeks done before the tragic accident, so that, as Admiral Truly testified yesterday, if this knowledge base had been in possession of, if this knowledge base that you've accrued after 6 weeks of brilliant and dedicated and highly professional effort had been available to Admiral Truly and other decision makers before the Challenger launch, that launch certainly never would have taken place. So since they had the knowledge that things had gone awry, why didn't they do over a period of several years what they've done very professionally and very successfully over a period of only a couple of weeks?
Mr. Shore, I'd like to start the answer to that question. As you know, once an accident has occurred, you can put your best talent and your large amount of resources in investigating that particular accident. Before the accident occurred, perhaps we should have been alerted, as you suggest, and then at that time...
Let me interrupt you, Dr. Fletcher. It's not a question of you should have been alerted. You were alerted.
I'm sorry, I didn't mean...
In 1983, information came up to NASA headquarters in Washington that things had gone awry. L. Michael Weeks signed a waiver of the fail-safe requirement for the joints, and headquarters was fully informed about the lack of redundancy in the joints. Then, in July of '85, in a memorandum from Irving David, it further shows that headquarters was again alerted to the seriousness of the joint problem. And in August of 1985, Michael Weeks and others at headquarters were briefed again about the repeated failures of the O-ring. So you were alerted. So this isn't just a problem of communications. There are plenty of fingers of blame if we're in the business of finger pointing. There are plenty of problems with decision making at Marshall. And undoubtedly they should have taken corrective action based on the information they had. But it seems to me that we cannot exculpate NASA Central Headquarters from a major share of responsibility here by saying, if they were alerted. You were alerted. Why didn't this effort, this remarkably effective and professional effort that we've done in a matter of 6 weeks, why didn't this take place in 1985? After the third warning that something was very much awry with the O-rings and the seal.
Excuse me, Mr. Shore, I didn't mean to say, if I did, that we were not alerted. I'm just saying maybe we should have taken that sort of intensive action at the time. And by the way, I think that your earlier statement is quite right. Headquarters was at least as much to blame as other parts of the organization. I don't think all the responsibility should reside just at the Marshall Space Flight Center, and I have said that, and I think everyone else that I know have said the same thing.
I'd like either you or Mr. Thomas to tell us how much did this effort cost that was made in the last 6 weeks to accrue this remarkably impressive database. How many people were involved in the effort? How much did it cost?
Here, let me try to answer that. We've discussed this within the task force, and there's not a lot of rigor in this number, so let me just try to give you a ballpark estimate. And if you're interested, I'll try to go back, or NASA will go back and try to
well, you're using up
get a good
valuable
estimate.
time, Mr.
But it's
Thompson.
about $5 million. About $5 million would be my estimate to run the tests that we conducted during this investigation.
During this 6 weeks?
During about the 6 weeks where we maximized the test activity.
$5 million.
That's a rough estimate.
How many professional and scientific people were involved in that?
In the conduct of the test and the analysis of the test, yes. I'd say in the range of 200 people.
Would the gentleman yield for a moment?
Well, of course
No,
I yield, Mr. Chairman,
no,
but I can't help remarking.
I'm going to give you more time than you expect.
I yield, Mr. Chairman.
I'm only trying to do something here, and I'd ask you to suspend on that, because otherwise I would be breaking the continuity of my own arrangements. What I'd like to do is ask Mr. Scheuer to suspend for a moment, because obviously these questions are going to lead in this direction. What I want to get on the record at this point, so we can be done with it, is there any other member that is here now that wants to ask a technical question on the basis of the data that we have before us? We had information that's been presented. We're not through with this, but that's the pre-launch and the other safety areas that follow. This is the heart of the technical testimony. And we've talked about the field joint. We've talked about the weather issues, the relation thereto. We've talked about the putty. There's other questions on the putty. We've talked about the high pressure. So what I'd like to do is use this time for any member in that order, first to get that on the record, so we are done with revisiting 50 times the same question over and over and over again, and then go from there and recognize Mr. Scheuer to begin, and then for Mr. Scheuer back to the gentleman from Texas, because he started in that direction. Therefore, the gentleman from Florida is recognized.
Okay. Mr. Thomas, now there seems to be an inconsistency, and I want you all, Mr. Thompson, to straighten this up for us. We had testimony. First of all, let me start with the commission report. The commission report says that one of the contributing factors is the fact that the casing of the SRB was out of round. And you all have measured this. You've measured it on a number of flights. Indeed, we find that there was an out of round on 61C as well. And in the way that you've presented the data to us here today, the way the commission has structured their report, that is an implication of one of the factors that contributed to the failure of the joint. Where the inconsistency comes in is that we have had testimony or information to our staff, specifically last Thursday at the Cape, from a Mr. Carver Kennedy, who says that once you mate the clevis and the tang, insert the pin, and then insert around the circumference 177 of the pin of the clips in the pin, that actually causes a circularizing in the joint, so that the implication is that you would eliminate the out of roundness once the clips are inserted in the pins. Now the question is, Mr. Thompson, Mr. Thomas, what is correct?
Mr. Nelson, I believe that the process you just described with the installation of the pins and the insertion of the shims. Shims.
Are you talking about the pin?
The pin.
Is that one and the same?
No, the pins
The
go
clip.
in- The clip.
Clip, okay.
Yes.
You call it shim.
Yes.
S-H-I-M?
Right.
Okay.
When you put those in, that tends to round it. But it cannot go all the way, because those shims are of a constant thickness all the way around, and they are not sized to take up the total amount of gap. So they're around the periphery of the vehicle. So it tends to round it, but it can never go all the way toward the rounding process.
Would the gentleman yield on that specific point?
Yes, I will. I want to, before I lose this, I want to make sure that the measurements that you gave us at the Cape last Friday, as well as today that you've repeated, where you show the differences in the roundness on the different segments, and you show that in the diagram of the circumference. You measure that out of roundness before you put the shims in, before you put the pins and the shims in. Is that correct?
Before we made it.
Okay. So conceivably, the shims then, as you just stated, will cause more circularizing or rounding once you put them in. Is that correct?
Yes, sir. To a degree, it is going in the right direction toward
Okay.
rounding.
Okay, so you're, all right, are you saying that by the putting in of the shims in the pins, that it does not completely correct the out-of-round condition?
Yes, sir.
How do you know that?
Because it dimensionally, the width of the gap of the clevis plus the width of the tang in the clevis plus the dimensional tolerance variations around the gap, around the circumference, in addition to the thickness of the shim, do not present a total even thickness of tang, O-ring, and shim equal to the width of the clevis. There is what I'll call a rattle space in there, a small space for the tang to move back and forth. And the thickness of the shims, 32 thousandths, plus or minus a couple of thousandths.
I thought the shim was 1/8 of an inch thick.
No, sir.
It's not.
No, sir.
With the gentleman here.
32 1,000ths.
32,000. That's this small clip I'm pointing to right here. It's 32,000.
That's 32 1,000ths of an inch thick.
Yes, sir.
Okay. So let me then summarize, and I'll yield to the gentleman. What you're saying is that when you put 177 shims in 177 pins around the circumference of the SRB segment, that it helps solve the problem of out-of-roundness, but it does not completely solve it, and it very well may be that you'll still have metal on metal.
Yes, sir.
Caused by the out-of-roundness of the casing.
Yes, sir.
Is that a fair summary?
Yes, sir.
And at the
I
same,
yield.
I thank the
Gentleman from
gentleman for
California.
yielding. And to follow up, at the same time that the shims do correct as much of the out-of-roundness as it's capable of doing, it creates, at the same time, a strain on the joint, in the metal of the joint, does it not?
Not perceptibly. It compresses where it is, where it
Well, any time, though, that you correct an out-of-roundness, you are creating some strain on the metal that is out of round when you move it toward roundness.
Yes, sir, and that, it does produce that, but it's not of a great magnitude. That's the only point I was making.
And that pressure between the metals, and sometimes where it even gets to metal, is what we have been shown to be the squeeze problem, create the squeeze problem. And particularly coupled with cold weather, that the O-rings have not the resiliency to return back to reseal when there is that squeeze as a result of the out-of-roundness or the stress of metal to metal.
It's the outer roundness.
Is the strain on at the O-ring point, or is the strain at other points in that effort to correct the out-of-roundness through the shims?
The only strain that one might see, and I think, again, it's imperceptible, is the amount of strain that you might put into the motor case wall by having it flex slightly to install the shim. The predominant squeeze that is put into place is squeezing of the O-ring, which does not induce any stress at all into the tang or clevis.
In the design of the O-ring, under these very conditions where we're trying to mate the two parts together, and if there is strain or if there is a round or creating of a roundness in the mating process with the shims, is there movement of the O-ring in there as that takes place, as the seating takes place, so that if there is strain, that the O-ring has the capacity to adapt itself to that strain?
The O-rings are are of course elastomeric material themselves, and they have good strain capability. But more importantly is they're completely covered with grease, and that grease will allow the O-rings to move as
So in the
as
groove
well.
that the O-ring is placed in, it can slide in that groove rather freely. It is not kind of pressed in there and locked into a single position without the flexibility of movement.
Yes, sir.
I thank the gentleman for yielding.
All of that notwithstanding, the state-of-the-art, as you've expressed it so well, it still is movable.
Mr. Chairman, I'm not through.
Just a minute now. The gentleman from Texas has a question, but I believe that you finished yet, the gentleman from Florida?
No, sir, I had yielded to Mr.
Okay,
Packer.
okay, all right. Well, the gentleman from Florida is
I
recognized.
just want to get some additional clarification on this. Okay, since you have told us that the measurements that were reported in this handout, that's not the one. There's a chart like that someplace where you've got each of the segments, and you've got the gap. And if I recall, in some it was 4 1,000ths of an inch. In others, it's 20 1,000ths of an inch. Is that correct?
Yes, sir, I think.
Right. But you said that is a measurement before you put the pins and the shims in.
Right.
Okay. Since we're concerned with the gap at the time of ignition, which is in fact once the pins and the shims are in, where do you have that kind of calculation? What is the gap then in inches?
We cannot tell precisely what the gap was at the ignition point of 51L. What we did during the investigation process was destack STS-61G. And our intent there was to, number one, we knew what the measurements were as we stacked the vehicle. And then before we began the destacking process and during the destacking process, we made several hundred measurements of all of the joints on the vehicle. And what our intent was to determine, number one, were we inducing any strains or unusual stresses into the clevis legs or other parts of the joint, and more importantly, could we predict where this maximum squeeze might take place? On the left hand, I believe, is the one that we spent so much time on. On the left hand, we determined that there was, in fact, some maximum squeeze, almost metal to metal on that joint, as would have been predicted based on the pre-mated measurements. But what surprised us a little bit is we could not precisely pinpoint its location circumferentially. It was dislocated 90 degrees from where we would have thought it would have been.
And in measurement of inches, what was that gap where you call it the maximum squeeze?
About 1,000th of an inch.
1 1,000th of an
Yes.
inch. And you interpolate from what you measured on 61G when you destacked, you interpolate that to 51L.
We think there was the same type phenomena there.
Okay, thank you, Mr. Chairman.
Chair recognizes the gentleman from Texas.
Thank you, Mr. Chairman.
Yes, go ahead. These are technical questions. This is the last technical question
No.
before the
My
chair
question is
recognizes the
not a
gentleman
techni-
from New York. Go
My
ahead.
question is not a technical question, Mr. Chairman.
No, this gentleman from Texas. Mr. Andrews, I beg your pardon. I beg your pardon.
I yield to my distinguished colleague.
I accept. My question is technical. On June the 11th, we submitted, the committee submitted some written questions to NASA. One of those I'd like to ask the group if you would expand on a little bit for us. The question was there a qualification test call-out in the design specs for the solid rocket booster joints? Your answer was there are no qualification test call-outs in the design specs for the joint per se. There are, however, design specs and verification requirements for the performance of pressure seals and the structural elements. Now, I guess the question is, were there any qualification specifications for the joint seals? Yes or no?
I did not pursue that particular question during the analysis process.
Well, can you answer that question?
Here, we're going to cover that a little later in Jack Lee's discussion, but in the qualification tests of the assembled motor, obviously that thing, after the firing in the inspection, then you should pick up any anomalies in that area at those joints.
All right.
Now, specifically what was done in the joint area relative to the qualification, I believe that's probably going to be covered in Jack's discussion in terms of what the specification calls for, what was done by test, and what was then augmented by additional analysis. So I believe if you can wait on that, we'll get to it.
Well, I'll be glad to wait to expand on it, but do you know the answer to the question? Is the answer yes or is it no?
Were there specific qual tests done on the joint? I'm not aware of them at a large scale, at the full motor scale, no. To my knowledge, there were not, just of the joint.
So your answer is no.
Well, here, let's just take a minute and let Jack come up and directly answer.
Thank you.
Would you repeat the question exactly?
We submitted a written question on June the 11th. The question was there a qualification test call-out in the design specs for the solid rocket booster joint?
Okay, the answer to that question is, in the design spec, there is not a specific qualification test requirement for the joint. However, there is a requirement for certifying that the joint meets certain specifications. You do this in a number of different ways. Qualification tests, you maybe do it by similarity, you may do it by development tests or analyses. So there is a requirement for certification of that joint, and there is and this joint was in fact certified to those requirements with some qualifications.
Well, just to be sure I understand, if you had a motor here, you're suggesting that there was a test made of the entire motor, but that in terms of the joint itself, the critical joint, no tests.
There was no qualification test. There were a number of special tests and development tests associated with the joint, but not associated with a full qualification, with the qualification to cover the full regime of all requirements. There were a number of tests performed, either in development, qualification, and special tests.
Okay. I'll be happy to yield.
Could you furnish the committee copies of all documentation of the qualifications for the joint?
Yes, sir.
And the criteria and certification? I'd like to have those.
Yes, sir.
Thank you.
Thank you. Thank you, Mr. Chairman.
All right, we'll have that filed for the record. Now we have just one.
Still on technical questions?
No. If the members would give the chair a chance, they've all been given ample opportunity to be heard, and I will get to the next witness. Yes, we're still on technical questions. What I'm trying to do now is to seal off the technical questions so we can go on and start from there to the processes that were handled. Now, the gentleman from Texas has concluded. The chair will now recognize the gentleman from Utah, Mr. Munson, who has a technical question he'd like to ask.
Thank you, Mr. Chairman. With regard to the field joint temperature, do you have a specified limit on as to what that can be before a launch is allowed to go forward?
Yes, that's my understanding.
It's a calculated temperature. It's not a temperature that is taken through some mechanical means.
For STS-51L, those temperatures are calculated based on an ambient measured value.
Obviously, those limits were not exceeded on that flight then.
To my knowledge, the the calculated limits were, or the ambient conditions were used for the launch process.
Now, the chart indicates that at the location of the leak, the temperature was somewhere less than 30 degrees. I don't know how to interpolate it exactly, but and it's my understanding that it was to be qualified to fly at 31 degrees. Is that correct?
Pardon me just a second. Was it 31 or 20?
Mr. Chairman, while we're getting the answer to that question, I thought it might help to point out that the reason between the conversation between the two gentlemen who were head of the task teams was the way we organized the investigation. Mr. Thomas's task team was to determine the cause of the accident, and Mr. Jack Lee's team was to get into the development and the production. In other words, the requirements, the certifications, and so forth. And so
I understand that, but we're bound to have a little overlapping, and we're going to tolerate and allow a little overlapping so that we can get on with it.
Yes, sir.
To a point. Now, are you finished, Mr. Munson? Are we waiting?
I need my answer.
26 degrees.
26 degrees.
Was the specification value, and the
chart indicates that it was somewhere very close to that.
The calculated value at the joints were approximately 28 degrees, thereabouts.
Now, you also indicated earlier that you've discovered that the casings expand after flights, and I assume that they don't return to their original size. Is that correct?
That is correct.
Does that in any way indicate that you will not get as many flights out of these casings as you originally thought you might get?
We don't believe that to be the case right now. We think that this growth that I have described is a function of the proof pressure testing, that is bringing the motor up to the maximum, in excess of the maximum expected operating pressure right after the manufacturing process to screen out flaws. Then in doing that, we think that after approximately the first 3 to 4 proof cycles that the growth will cease to exist, and then they can be used as usual throughout their normal life.
You don't have any experience in that area though yet, is that correct?
We have not completely resolved that issue.
Thank you.
All right, thank the gentleman. Now, yes, now just one second. The gentleman from, I'll give the gentleman from California an opportunity in a moment. Mr. Lujan from New Mexico, please.
I am confused as to what Mr. Lee's answer was. My understanding, in part of your briefing, will show qualification not accomplished to the required spec limits. My understanding was that there was no analysis made on the effects of temperature on that joint. That Thiokol was supposed to do an analysis, but that when you went back and checked all the data, you found that that analysis had not been made. Now, did I understand your answer just a little bit ago to Mr. Andrews that analysis had been made?
Sir, could I defer that until Mr. Lee comes up immediately following me? That's
well,
part of
he's
his
answered the question, and it apparently is completely different than what my understanding is.
Chair would ask Mr. Lee to come up here now because this is in limbo. Let's get it squared away right now.
Okay, let me go through a little more explanation. I understand some of the confusion here. There is a requirement on Thiokol in the contract, in the specification, to certify, design and certify the joint to a number of requirements. Now, to certify, you can do that by qualification testing, development testing, special testing, or by analyses. In the case of the seal joint per se, the requirement to certify, if you will, the joint to the full range of specification requirements imposed on them, and this is by a Johnson Space Flight Center document which is imposed on all of our contractors. It's around a natural and induced environment. The natural environment requirement ranges from 31 degrees Fahrenheit to 99 degrees Fahrenheit. The induced environment, which means after you've got the external tank loaded and so forth, this can range from, under those same environmental conditions, from 26 degrees Fahrenheit to 120 degrees Fahrenheit. Now, in reviewing this process with THIACOL, they did not interpret these requirements, either the induced requirements or the environmental requirements, to mean for vertical flight. They interpreted these requirements to be in a storage configuration. If we, and then to take it one step further, in reviewing each of how they satisfied each of these, or all of their requirements relative to performance, sealing capability, and so forth, we found that an overall performance of this joint was required to be demonstrated by qualification tests, by development tests, and by flight tests. That requirement was associated with a temperature of 40 degrees to 90 degrees mean bulk temperature of the propellant from sea level to 200,000 feet. That's an overall system requirement. We didn't take issue with that. There's a requirement for the sealing capability, by the way, and they did in fact qualify these. They did it with about 6 demonstration motors, full-scale motors, and 3 or 4 qualification motors. And the lowest temperature of any of those was, I believe, 36 degrees. Another requirement for verification of this seal was associated with the sealing capability of the O-rings themselves. And this requirement did not impose a temperature limitation, if you will, but it was more to demonstrate that the O-rings did in fact seal, they were redundant, and that there had a leak test port to be able to verify, and from an acceptance standpoint, the integrity of these seals. The third part of this system specification, if you will, has to do with the imposition of the natural and induced environment, so the 31 to 99 and the 26 to 120. This was specified to be accomplished by analyses. Now, the contractor proposed that, THIACOL, and the Marshall Space Flight Center accepted that. The issue comes in on the fact that they did not interpret that to be an in-flight requirement. They did not do a detailed analysis or test to verify that during the flight regime. There was, in fact, analyses done that turned out to be, in hindsight, and in light of the issue of the lack of understanding of the joint, the temperature issue and so forth, the analysis that was performed, it was not adequate. And I think the Commission report points that out, not specifically about this issue, but the inadequacy of the overall certification and qualification program. The analysis that was in fact performed was the review and assurance by inspection that the O-ring material itself, met a certain mil spec, and I have that number, but a certain mil spec. The significant part of that mil spec is that it should be able to be usable from a temperature range of -30 to 500. And on that basis, they considered that analysis as a part of an analysis which should in fact qualify or certify that particular joint. So the issue here, if you want to look at the uncertainty of why this issue was brought up relative to the qualification, is that in light of today's understanding, that was not adequate, and the fact that the THIACOL Corporation misinterpreted or did not interpret that range as the NASA did.
Mr. Chairman, you're pushing me, and that's fine, so we can move on ahead, but we'll pursue that this afternoon.
Okay. Yeah, I would suggest the following. We're getting out of kilter here a little bit, and we've had a good continuity and want to keep continuity. I knew this was going to happen in part as a question of when. There are obviously other technical questions that other members wish to ask, and the chair is going to see that every single member's opportunity and his interest or her interest is respected. It is almost 12:30, and as I promised I'm going to do, I'm going to defer now to my good friend from New York, Mr. Scheuer. When Mr. Scheuer is concluded, we will break from our hearing, return at 1:30. If Mr. Scheuer needs additional time at 1:30, he will be up number one. If he wants to suspend and wait for other members to bring more of the technical matters out, that's what we'll do. And the second point, as far as our witnesses are concerned, we will then defer to Mr. Lee, because I see it's now important to bring in your next phase because it's overlapping, and I think that's in fact, I don't think that is the direction we will follow. The chair now recognizes the distinguished gentleman from New York who's been eminently patient,
Well, thank
the
you, Mr.
distinguished
Chairman.
Mr. Scheuer.
I must confess, I have a sense of abiding inferiority at not being able to cope with all these technical and scientific questions. I've never.
The redeeming factor is you have the floor.
Well, I've never been very good at science or math. As a matter of fact, I have to take my shoes and socks off if I want to count to 20. But here we are, and let's get back to some of the policy questions we've all been wrestling with. I think we were discussing a few minutes ago that since the accident 18 weeks ago, and since the task force on the O-rings was set up, in over a 6 weeks period, we spent about $5 million and about 200 scientific and technical personnel, produced this extremely impressive body of evidence that we now have that really answers an awful lot of questions about the O-rings and the failure to achieve adequate sealing. Is that more or less what we've decided?
Yes, that was my estimate in terms of
Very
the
good.
resources.
And I think the record also was clear, and I think Admiral Truly testified to this yesterday, and without putting words in your mouth, I would assume you all agree that if we knew before the launch what we know now, after this expenditure of $5 million achieved, that was put together, this technical knowledge base by 200 scientific and technical people, that there never would have been that tragic launch. Okay? Now, what I'd like to ask is the perfectly predictable follow-up to this. After the repeated warnings of maybe 14 or 15 failures of the O-ring on a number of flights, and after these 3 warnings in February and March of '83, in July of '85, and in August of '85, warnings that went right up to NASA's Nerve Center in Washington, how much in the way of resources, both funding and personnel, did you apply to solving the perfectly self-evident problems of the seal and the O-rings before launch?
Mr. Scheuer, I'd like to start out again on that one. Even though I wasn't here, I think we want to differentiate between dollars and numbers of people and the quality of people. Yesterday we talked about giants, the new giants in NASA. Well, the folks that are here today are those new giants. Admiral Truly has picked people from all over NASA to do this investigation, and these are truly unusual people.
With all respect,
now, answering
Dr.
your
Fletcher.
questions, sir.
Yes, let's get to the
I think
specific answers.
we very likely should have, with all those alerting signals, put that kind of talent, because it was available.
Well, I'm
in
asking a
NASA.
simple question. I'm asking how much in the way of funding and how much in the way of personnel, scientific and technical personnel, was applied to develop specific answers to the problems of the failed O-ring that had appeared on a dozen or more launches, and that information about which was conveyed at least 3 times to NASA headquarters in Washington. What was the specific response to that in terms of funding to find the answers and application of scientific and technical personnel? How much? How many people? How many dollars?
Well, if we don't have anybody here that can answer
Well,
that
now,
question, we'll
Dr.
supply
Fletcher,
it for the
with
record.
respect, you weren't there, and these
Yes.
folks were there. Why don't we give them a chance
Fine.
to answer?
Well, there was one of the 4 of us here.
Mr. Thomas, looks like the bee is on you.
As I understand the question, sir, you're asking after the period in mid-1985 when the presentation was made to headquarters on the seriousness of the seal situation, how many resources were applied between then and January on trying to fix the seal?
You had a big fat question mark that was articulated on 3 different occasions, warnings coming from Marshall to NASA headquarters in Washington, in early '83, in July of '85, and in August '85, that described at least a dozen failures of the O-ring. Now, what did you apply in the way of resources, both in trained scientific and technical personnel and in dollars, to remediate that problem before the tragic launch 18 weeks ago?
I'm sorry, sir. I think we're going to have to present that for the record because the people that have to provide that are not in the room today.
Well, Mr. Chairman, I would request that the people who have that information be invited to be requested to testify.
Well, I think the gentleman makes a very valid point. In view of the fact that we're going to break shortly, is there a possibility you could contact some of your folks and maybe put something together for this afternoon?
We'll do our best, Mr. Chairman, between lunch hours.
Yes. I would just like to make one more comment. Apparently, there was a redesigned task force on the O-rings at Morton Thiokol. There was a redesigned task force on the O-rings at Morton Thiokol.
Yes, sir, I understand.
I want to know what they had in the way of funding and what they were able to put together in the way of trained manpower, scientific and technical manpower, to address this life-threatening problem of the O-rings and the joints between the 3 warnings culminating in July of '85 and August of '85, between that point in time and the time that this tragic launch took place. What kind of resources were made available to Morton Thiokol, either out of their own funding or out of separate, perhaps emergency funding of some kind, discretionary funding of some kind, to remediate this problem?
Yes, sir.
And I have to just pinpoint that or footnote that by saying you really have achieved a notable knowledge base in the 6 weeks that you worked on the problem with insignificant resources. I don't know how you would quantify the cost to the American public of this tragic disaster, leaving aside the acute pain that we've all suffered from the loss of those 7 noble, great Americans. But just looking at it financially, as against the $5 million cost of preventing it, the Challenger, the hardware itself cost $3 or $4 billion, and if you crank into the computer the additional cost to the public and to NASA, the delay in the program, the upset, the loss of morale, all of these intangibles, you would probably come out to $5 or $6 billion. So you're talking about a cost benefit, what would have been a cost benefit calculus of 1 to 1,000. If you'd spent that $5 million before, you would have saved $5 billion afterward. And of course, those 7 great lives. So you can see the point that I'm getting to. Why didn't we spend this $5 million, and why didn't we have these 200 scientific and technical people assigned to this problem after the ample repeated warnings that NASA Central Headquarters had up to and including August of 1985? What went wrong? What went wrong, and why didn't we make this remedial effort before the launch instead of having this excellent scientific attack on the problem that was perfectly self-evident before launch after the tragic event, after the horse had fled the stable? And this is the information I would like you to get us this afternoon.
Right, well, we'll defer that to this afternoon. I'd like to just put one more technical question on the table before we break, so for continuity. We mentioned, Mr. Thomas, relative to the burning of the NRB insulation. From NASA's drawings, the insulation is in contact with the burning propellant. What evidence is there from previous flight exhaust gases that the insulation burns? Is there any?
From the past static motor test, I I would presume there to be none, but from lab tests which we conducted during the investigation to determine the materials that were present in the joint, which one of those would burn and which would produce back smoke. The NBR is the one, and the grease are the ones that produce black smoke.
So that's been ascertained since you've done your investigation?
Yes, sir.
Okay, thank you. The chair now calls for a recess. We'll return at 1:30. And may I suggest to members, please be here on time, if you will, because we're going to begin immediately at 1:30. And we'll begin with Mr. Lee in your presentation at 1:30. The committee will reconvene, and as announced this morning by the chair, our afternoon session will be devoted initially to a presentation by Mr. Jack Lee from NASA, followed up by Mr. Holloway from NASA, and then Mr. Utzman from NASA, which brings into then to clear focus the items and the areas of expertise and study that the different task forces have carried out in the review of the accident and other peripheral data. Having said that, the chair recognizes the distinguished gentleman, Mr. Jack Lee from NASA.
Thank you, Mr. Chairman. Thank you, Mr. Chairman, and members of the committee. Could I have the first view graph, please? The second. With your permission, sir, I'd like to follow the agenda as displayed on the screen.
Well, wait till we get the lights out, somebody around here. And I think it would be helpful, Mr. Lee, if you would pull your microphone closer, please.
Yes, sir. First, by introduction, I would like to give the organization which we used in accomplishing this effort, and the review schedule which was we used during the process. Then a little on the review approach for our team, and then I would like, in way of indicating the findings, I would like to present the significant findings of this team. Now, we did not make recommendations. We came to findings. The next view graph, please. The commission members on our team were made up of Mr. Joe Sutter, who was the lead for the commission. He is from the Boeing Aircraft Company. Dr. Arthur Walker from Stanford University. Mr. Robert Rummel, who is now consulting and has been with an executive with the TWA. Dr. Gene Covert from MIT, and Mr. Al Whelan from Hughes Aircraft. Can I have the next view graph, please? By the way, in the way of support to me in supporting This team, I utilized primarily a small staff within the agency, plus predominantly the project offices within the Marshall Center and the Johnson Space Center. The contractor visits, by the way, the approach we took was to visit each of the contractors to accomplish our mission. Plus a visit at the Marshall Space Flight Center and at the Johnson Center. On the 5th of March, we had an introductory session at Johnson, primarily to familiarize the commission team with the overall requirements, the Level 2 system requirements as imposed on the shuttle program, and how they are divided to be introduced into each of the elements of the shuttle, the elements being the orbiter, the external tank, the shuttle main engine, and the solid rocket boosters. We started our contractor visits first with THICAL, and we were there on March the 17th and 18th. We were at Rocketdyne, the developer of the shuttle main engine, on April the 2nd and 3rd. We were at Rockwell on the 3rd and 4th of April, primarily to discuss the orbiter. At Marshall Space Flight Center, where we reviewed a number of specific questions that had been posed to us in advance by the commission team members, and to review the solid rocket booster portion of the solid rocket booster, if you will. As to distinguish between the solid rocket motor and the solid rocket booster, the motor is per se the propulsion system. The solid rocket booster includes the recovery system, the avionics, the thrust vector control system, and that sort. On the April the 8th and 9th, we visited the Martin Marietta Corporation near New Orleans, and that was for the external tank. The review approach we took, since we were primarily interested in looking at the production and development aspects. Next slide, please. We were specifically looking at the production and development aspects of the shuttle in its entirety. As that effort could have been related to the accident. You have to recognize that we were performing this somewhat in parallel with the analysis effort, and it was not the conclusions from that Mr. Thomas presented earlier were not available to us at that time. We did this in parallel. So what we were looking at is specifically the concept or the approach to establishing design requirements, how these requirements were controlled, the review process, the certification of those requirements, the development and qualification. That means development meaning component and subsystem testing, as opposed to and verifying design parameters, if you will, as opposed to qualification of an entire system to meet specifications. This also included the transportation mode, since the solid rocket motor segments are produced in Utah, and they have to be transported across country by rail to the launch site at the Cape, and how not only the transportation mode, but how this transportation mode was verified. We looked into the design and production control, the manufacturing aspects of these elements. In addition, we looked at the launch services, how the development contractor becomes involved and with the launch activities, if you will, and overseeing his hardware and introducing requirements and ensuring that the tests and acceptance and checkout requirements at the Cape, in fact, are met. One of the areas that we knew that we were concerned about from at the time we started in March was the critical items list. We reviewed the CIO, by the way, is critical items list. FMEA is a failure modes and effect analysis, and hazards analysis is, in fact, a hazards analysis. Our intent here was to understand and to recognize and to comment on, if necessary, the process for which these failure modes and effects analysis were generated, how they related to the identification of a critical item and what category of critical item it was, and then how that dealt with the hazards analysis. The last item was in response to a number of specific questions that were, in fact, submitted to us in advance of the start of this process. Could I have the next view, please? We knew, we'll start now with the significant findings. and with the solid rocket motor in particular, and these were findings that resulted from our review at the Thiokol Chemical Corporation in Wasatch. We knew, of course, that by March that the solid rocket motor was pretty well implicated in the accident, and we were, in fact, aware of a lot of things that had gone on by that time, recognizing that the failure analysis had been proceeding for about 2 months before this. So we were aware of the fact that the solid rocket motor was very much involved. So we did, in fact, and we knew, by the way, that it was pretty well isolated. It could be isolated to the joint area. We thought that was the case. So by having that fact and recognizing it, our charter to look into the design and development or production development aspects of the solid rocket motor, we were more thorough in reviewing not only their whole process from a development standpoint, but specifically we focused on the solid rocket motor joint. So we took as examples to verify or to prove the approach to the development process. We took as examples how they dealt with the joint, how they from a qualification, certification, verification standpoint. So we were in fact more specific in that area, and as you might expect. The significant findings that at the solid rocket motor, with the solid rocket motor at Thiokol, the first one has to do with the subject we discussed this morning, and it has to do with the qualifications of the motor. That's qualification testing was not accomplished to the required specifications. And I gave you I attempted to give you an explanation of the process from the requirements introduction by specification, the method, identify the areas that require certification, and the method to be utilized for that certification this morning. Maybe if I can give one more example, it'll help clarify this thing. In the classically, the best thing we could do to ensure that entire motor was qualified, completely qualified to all environments, would have been to encase it with an environmental chamber, if you will, taking it to the lowest possible temperature that had been established, and introduce, as we fire, the actual loads, lift-off loads, if you will. Now that did not, and that would then, if we accomplish that full-scale testing, that would in fact have qualified tested the entire motor, including the joint. Now, the way we did this, because we didn't have an environmental chamber and we did not determine it to be necessary to have an environmental chamber, we qualified the motor to the environments that were available to us. And by the way, this did range from some 40 degrees to close to 90 degrees. So we were in the area of most concern, that is the mean bulk temperature requirements. We did, in that same logic, in order to be able to certify that the joints did meet the requirements, we chose to do that by analysis, and I explained that this morning. We chose to perform that analysis, and in that analysis, we used the specification for the O-ring, which does specify it can be used from a range of minus 30 degrees Fahrenheit to 500 degrees. Now, the issue, the reason that that issue was brought up is in today's environment, the thing was not qualified, tested to that full range as I explained, and based on the interpretation of the specification by Morton Thiokol, enough effort, I would say, did not go into completing this complete verification by analysis, and again in hindsight, you would say that our selection process, and that would be NASA's involvement here too, the selection process for that analysis was somewhat inadequate. The next point is the adequacy of the O-ring process and quality control. Now, we did not find in our investigation, nor did Mr. Thomas find in his analysis investigation, that the O-rings used in this flight were in fact not acceptable, or were not of good quality control, nor that they were not properly processed. But in our reviewing in detail this process, we found it had not been identified as a critical process, which we believe it should. And there were a number of things that in areas that we believe could be changed to give a better assurance that in the future that that O-ring did in fact get processed properly, and that there was no way that you could have a quality escape, if you will. Now again, I'd like to remind you, we did not find any place where we had an improperly processed O-ring, but the process itself, and we felt we had that charter to look to that, and so we did in fact believe, or in fact I'm not sure that's a particular recommendation that came out, but we did feel strongly that that process should be beefed up. The next point is questionable where the horizontal hot fire testing compromises flight simulation. Now we knew of this possible concern on the part of Mr. Sutter's team early, so we have started a month or so ago a pretty detailed evaluation of the merit or requirements, if you will, first of whether the solid rocket motors should be fired in the vertical or horizontal, and in doing so, we're assessing facilities available around the country. We're looking at the requirements which we are trying to impose on ourselves to ensure that the motor is properly qualified, and we're weighing these to determine which we believe would be the proper route to go. That once we complete this, we will make this information available to Admiral Truly, who in turn will make a decision on on that part of the future testing of the solid rocket motor. The next item is in the somewhat same category, but it's a little different. There's a difference. There was in fact a potential difference between the certification testing and the flight configuration, and specifically, what happened here is when the motor is installed in the vertical, there's some adjustments or changes, if you will, in the famous putty configuration. It tends to not assume the same shape necessarily that it would when the vehicle is stacked in the vertical. And by this we mean that when we're ready to static test the motor, it would not be in the same configuration we assumed it would be in the vertical. So there was some adjustments, if you will, some tapping of the putty, some fixing of the configuration, which we believe could in fact make a difference in the results of the static test. The fourth item is in case reuse. Now we did not find this only with this production development team. We had the benefit of some of Mr. Thomas's earlier analysis, and the situation which exists here is by going back to remeasuring cases which had been reused. Now these are the solid rocket motor cases. If you remember, once we fire these, we bring the solid rocket motor back in, and as part of the refurbishment, we clean the motors out and we recast, if you will, the propellant. We found in measuring some of these reused cases that the dimensions had changed. Now this was somewhat of a surprise to us because it was not anticipated and understood that this should have happened during the reuse. Our understanding of the characteristics of the material, the way it was processed, should not have allowed this change in dimension. Now let me quickly to say that in Mr. Thomas's analysis and our understanding of this dimensional change, there's no clear or no indication that the reuse of the possible growth of cases due to reuse had an effect on 51L. But it was characteristic of a change in the cases, and it's something that was of surprise to us or change to us, and we recognized we had to make the determination. We are in the we think we understand this, and it is being properly analyzed now, and I have no doubt that we will solve that problem of the lack of understanding of case reuse. The next point is inadequate understanding of the field joint operation as designed. We came to pretty much the same conclusion that Mr. Thomas's analysis team arrived at, and he did his through additional testing and analysis and development testing, if you will. We came to that conclusion by just assessing the design and the process and the understanding as the design was as the joint was designed and tested. The last item is the case configuration changes resulting from transportation in the horizontal. Because of the length of these cases when they are cast, we transport them cross-country in the horizontal position. As they stay in the horizontal for long periods of time, the case tends to become oval. Now, we think that this is a potential contributor, this becoming oval, when it gets to the Cape, to the possible out-of-roundness. Now, we've seen in the Commission's report an address. This is addressed where there's some consideration for that, for either fixing the transportation mode, or being able to properly assure that the roundness is in fact adequate or correct prior to stacking. You have the next one, please. The next area is that for the shuttle main engine, and this is the findings or significant findings we arrived at from our review at Rocketdyne. We found that the engine itself is a high technology, high power density, state-of-the-art engine. Very, very precision instrument. We found that there was because of this and because of the long relationship, I guess, in working with liquid propulsion engines at the Marshall Space Flight Center, our people at NASA and that of the contractor had a very good understanding, not only the programmatic but the technical requirements. The third item was a consideration for margins of critical components that were not demonstrated by test. Now, this does not have to do with the acceptability of the certification for flight. Our concern here is over the long reuse of the engine. We believe that we are going to have to develop or introduce some tests that will allow us to, by actual test results, recognize the margins that are in some of these components. The way we do it today is we test around the nominal, and we analyze or compute what we think those margins are. We believe that we're going to have to extend our test program in the margin area to be able to recognize these margins. As such, we will understand the performance of the engine better as it relates to performance over the long period of time, the possible reuse, the overhaul, the refurbishment of engines themselves. Can I have the next one, please? At Rockwell on the orbiter, we also found that there was a very good understanding of the programmatic and technical requirements between the NASA and Rockwell. We also found that the Rockwell had some concern relative to the level of involvement that they had with the orbiter as it's processed and turned around, if you will, at KSC. And the emphasis here was more of involvement in that process in a way that their technical knowledge, their background, their corporate memory of from a technical standpoint of the orbiter could best be brought to bear on any potential problems or foreseeable problems on the orbiter itself. The next item was a number of critical components, and I listed two because they've been used before, the 17-inch disconnect and the brakes. There was a list of these. A number of components which within the orbit, and this, by the way, is not only in the orbit, there are some others in the SSME, there are some in the external tank, and I'm sure there are some others in the SRB, which we will ferret out. But in particular, there are a number of critical components like these that require some reassessment. This activity has already started. In fact, it had started before the accident. The last one has to do with, again, a concern on the part of Rockwell that the critical payloads, like the Centaur, which are relatively hazardous because of they are, in fact, cryogen propellants within the orbiter bay, possibly we're not receiving as much of an overall safety system assessment as you look at the orbiter in totality with the payload attached. And in order to be able to assure that all safety aspects were covered. These, by the way, in fact, all of these findings have been, actions are being taken by the Orbiter Project Office at JSC to start effort on these. Can I have the next one, please? The last one is the external tank. We also found there was a very good understanding by both NASA and the Martin on program and technical requirements. Martin had some concern, not quite to the degree of Rockwell, that they didn't have not quite the direct involvement at KSC on their hardware, if you will, their hardware, meaning the development contractors' hardware. They did not have the same involvement or adequate involvement that made them feel comfortable that everything was being, that happened to that hardware, in fact, was getting the proper assessment, again, based on their knowledge through the years of development qualification. There was no problem, by the way, identified by the Martin people, though. And then the last item has to do with the range safety destruct system. Today we have range safety destruct system on both SRBs or both SRMs and the external tank. And this has been a question that has come up over the years, and we are in the process of working with those people who've established that requirement. And if we can safely, or if within bounds or within the requirements established, if we can eliminate a destruct system, if you will, from the external tank, I would say we all feel more comfortable about that. That concludes the significant findings. I would like to summarize with one point. We did not find in any of our reviews with these contractors a real deficiency in the basic processing of establishing an identification of requirements, how those requirements are introduced by contract, how the specification identifies those, the requirements for certification and verification, the configuration control, acceptance. We found that the procedures, if you will, the mechanism for being able to accomplish the production and development programs of all of these vehicles were, in fact, sound, and only in some areas where that has appeared to break down, similar to particularly in the case of the qualification testing, and I won't say that exactly broke down. It was some misunderstanding, and possibly, like in light of today's environment, we may have, or should have put more emphasis on the certification aspects of that seal. But the procedures and the implementation of these procedures seem to be sound throughout all the contractors.
I thank the gentleman. I'd like to hear now from the report from Mr. Holloway on mission planning and operations. We welcome Mr. Holloway. Go ahead with your presentation, please.
Mr. Chairman, thank you. First chart, please. Second chart, please. I'm reporting on the mission planning and operations team, and first I'll introduce the members of the presidential panel of the same title. Dr. Ride was the leader of that group. Mr. Rummel participated, Mr. Holtz, and Mr. Atchison. Next chart, please. First, let me characterize what our group did, the Mission Planning and Operations Panel. There was not a focus for our group because there was not any obvious relationship to the accident itself. So we were in the process of looking at a large number of activities that go on in the process of preparing for and executing the flight operations during the shuttle mission. And as such, we established a fairly large group of individuals to go off and examine multiple areas in flight operations to see if, one, we could find anything that contributed to the accident, and secondly, if we saw any indicators in those functions and activities that needed attention to prevent future accidents. First, I will say that I will not discuss each one of these things in detail today because I don't think they are important for what's your purpose here. But I would like to characterize generally what we did find. First of all, that we did not find any concerns that were a total surprise to the system and the people that were involved. I would characterize what we did find in three ways. First, there were many of the areas that we examined that we found that all was proceeding very well for the medium to high flight rate that we were looking toward, and the procedures and processes were working very well. Secondly, we found situations where the functions and activities may not have been what we would like for them to be for a medium and high flight rate, but the procedures and plans and budgets were in place that would allow that to evolve to more than a satisfactory situation. And the third area were areas of concern that perhaps require some emphasis on the part of the program as we go forward to ensure that that it evolves properly, to ensure that we have everything in place that we'd like to have. Next chart, please. I might add that the dominant portion of the activities we looked into fell in the first and the second category. We met with the Presidential Commission 11 times, presented 22 formal briefings and numerous data package and formal reports. That amount of time spent with that group was on the order of 65 to 70 hours in technical briefings, and some 320 to 350 people at one time or another participated in the generation and the presentation of that information. Starting at the top, we discussed with that group the 51L mission preparation, including the crew training, the crew activity planning, the trajectory design, the ascent abort modes, and how that worked out on 51L. We also talked about payload, our cargo manifesting, and provided an opportunity for the SR and QA people to be interviewed on March the 12th. March the 20th, we had a joint session to put together plans and schedules. On March the 24th, we discussed the range safety history that Mr. Lee had previously discussed briefly with you. The history of that program, how it evolved on the shuttle itself, what the current procedures are, what the flight rules are that control its utilization, and where we are today. We discussed the milestone history, in other words, how well we had been doing with schedules in terms of mission preparation and how we anticipated we would be able to perform in 1986 had that flight schedule been allowed to evolve. We reviewed our weather flight rules, RTLS rain damage assessment, and again on March the 25th we provided information on shuttle main engine failure containment, and an opportunity for the Commission members to interview some safety, reliability, and quality assurance personnel. On March the 31st, we reviewed orbiter testing, what we thought the operating base was for the flight operations group, payload safety, crew training, and the state of our crew procedures program that maintains flight crew procedures. On April the 7th, we participated in a meeting at Marshall again to allow the Commission to interview some SR and QA personnel in that location. April the 8th, we reviewed workload assessment, how much overtime and how the annual leave was being used and so on and so forth for particularly the Mission Control Center personnel in Houston. We reviewed the state of the orbiter software program and how we develop software and test it and prepare for each flight. Reviewed cargo manifesting, the process and procedures associated with putting a cargo together, and the history of how well that's gone and how many times we have changed those cargoes and those payloads as a function of each flight. On April the 9th, in a 9-hour meeting, we reviewed the landing considerations, KSC landing considerations relative to rain and brakes and nose wheel steering, and also transatlantic abort landing considerations of the same nature. On April the 14th, we reviewed the ascent envelope expansion, or the state of the ascent envelope in terms of of flight design and trajectory, and spent the afternoon reviewing the history of the first stage abort options from the inception, RFP days up through 1983. And on April the 15th, we provided an opportunity for the Commission to review, continue their review on safety, reliability, and quality assurance. Next chart, please. On April the 18th, we submitted to Admiral Truly our report. It was later submitted to the Commission by Admiral Truly's office. I won't review those in detail, but it included all of those things that I've previously discussed. Now I'd like to review the major findings of the group, and before I do that, I need to tell you that they are not all related subjects, so they don't flow very well. They are all individual subjects, or most of them are individual subjects, and as such, they don't have continuity one from the other. First, under mission planning and preparations, the 51L mission was manifesting, and mission operations, flight crew preparation, pre-launch and launch were typical and satisfactory and had no effect on the accident. Furthermore, the flight crew and the ground crew were well trained. They had fulfilled all of the training requirements. And more importantly, we all believe that the crew, both ground and flight crew, were indeed well trained and well qualified to fly the mission that would have occurred had the accident not happened. Under 51L mission preparation, first, there were no actions possible that could have resulted in the survival of the 51L crew. As has been stated before, during first stage, the SRB simply must work. There's no possible procedure that can allow us to separate from a thrusting SRB with the current configuration that would allow survival of the orbiter. Secondly, the range safety system that Mr. Lee had previously discussed did not contribute to the accident. And the actions of the range safety officer were important. As you remember, the range safety officer destroyed the SRBs in flight, and he took the proper action based on the conditions of the day and the situation that he had on his hands at that particular time. Also, we have initiated a joint NASA-DoD review of the range safety system, and we will be reviewing those issues, many issues in that system, including the one that Mr. Lee discussed earlier today. Under NSTS mission planning, we found that the Operations Maintenance Inspection Program, that's the program in which the requirements to inspect and maintain the orbiter, from structural equipment to line replaceable units, and the process of getting those requirements introduced into procedures at KSC that the technicians can execute, including a methodology that allows the feedback to the appropriate people to, when in terms of accomplishment of those procedures were immature and did not provide what we would like to have in the future, to make sure that all the requirements are met, and in such cases when waivers are entertained, that they're identified very early in the process and can be dealt with at the technical level in time to make timely decisions. That work has been in progress for a year or so at this time, and we expect that it will evolve satisfactorily in the future. So it's a matter of emphasis and completing the work that was in progress at the time of the accident. Under NSTS mission operations, one of the major findings was that the current program commitments precluded devoting adequate resources to developing a capability to support the increasing flight rate. And what I mean by that is that that either because we were more interested in flying the flights or because the flight rate demanded all of our attention. We were spending all of our resources toward flying, a majority of our resources at least, toward flying the flights rather than looking toward the future flight rate and the requirements that it would take to develop the flight products and the procedures and the details to fly at the higher flight rate. Additionally, at the time of the 51L launch, KSC landings, one of the favorite subjects has been discussed by many people, did not constitute an unreasonable safety of flight risk based on known failures. Next, statistical weather and forecasting uncertainties have resulted in several wave-offs from KSC and dictate a need for multiple landing sites for intermission. We will always need multiple places to land the shuttle, regardless of what the planned landing site is, and we ought to put those in place and have plans in place to utilize them and turn the vehicle around and prepare for the next flight. The next item speaks to the current landing and deceleration systems have not demonstrated an adequate margin for routine KSC and transatlantic abort landings. We believe for a long-term program, we need a better landing and deacceleration system, and in fact, the program has in place many of the elements of what we believe are required to cause that to happen. Crew escape systems, we reviewed the history of the crew escape systems from the inception of the RFP back in the early 1970s through 1983. And there's very many different varieties of crew escape, including augmenting the basic shuttle to allow it to perform a recovery type operation and land on a runway, from ejection seats to escape pods to situations where in glided flight a group of crewmen might bail out of an opening in the cabin during glided flight before impact. During that review, we found that these systems were all reviewed numerous times throughout the history of the shuttle program, and because of what at that time was considered to be limited utility, and what I mean by that is that the systems that were envisioned to be put in place would not cover adequate number of the envisioned scenarios that might happen, such as 51L, that it was not found to be a usable system. The technical complexity, the ability to build such a system, and the ability to monitor the impending failures and execute the escape system in time to make it useful, and cost and schedule and performance impacts being primarily payload to orbit, no system was implemented. Last in this group, we reviewed the astronaut office involvement in the program and found that they play a significant role in all activities associated with the development, flight preparation, and flight execution. And they or their management are members of all major decision-making boards and panels. Under flight rate and scheduling, we found that the 1985 mission operations were successful in spite of significant manifesting perturbations. We did take on a number of challenges in 1985 outside of the scheduled manifest, and we had a number of upsets, one including an engine shutdown on the pad, remanifested the cargo and flew a new mix set in a matter of 6 or 8 weeks. We took on the challenge of flying the 51I mission and rescuing the Navy CENTCOM satellite in about 4 months, and executed that, and in my opinion did all of that quite well. However, the trends indicated that the milestones required to support the preparation for the 1986 flight schedule would have been extremely difficult. We may have arrived to the point where our schedules did not meet our capabilities. We had 4 major conclusions that that coincided with those 11 major findings. First, we believe the NSTS program should develop a bottoms-up strategy for expanding our flight rate, and as a start, rigid manifesting criteria need to be established and enforced. Also, we believe an inspection and maintenance program should be implemented that will ensure that we get the job done as long as the shuttle flies, and work is in progress to make that happen. Thirdly, the NSTS program should focus attention on defining and providing an adequate margin for end-of-mission and intact aboard landings, and that work is in progress, and it includes both ground facilities and flight hardware. And last, the program should evaluate the options and utility of providing crew escape systems and augmenting orbiter abort modes with using the technology of 1986 with the understanding of the program as we know it today. Thank you.
I thank you, Mr. Holloway. Now we'll hear from Mr. Utzman, who is the final witness on the pre-launch activities team. Mr. Utzman.
Thank you, Mr. Chairman. First chart, please.
Includes approximately.
Next chart, please. This chart depicts the organization that we used in order to carry out the task of supporting the pre-launch team of the Commission. The pre-launch team job was essentially in three areas. One was to look at the NSTS processing that had been done for 51L. The second part was look at the flight readiness processes that led up to the launch decision. And the third area was to look at the security aspect and determine if there were any problems in that area. In carrying out those three tasks, we organized into three teams, as it's shown on the chart. On the chart, I would like to say that the purpose was always to support the Commission's activities, looking for causes of 51L problems, since this activity was primarily started immediately after the accident. But we also realized that due to the comprehensiveness of the review, that there would be many lessons learned and many things that we could find that may not be associated with the accident, and we wanted to capture those so that we could use those and make improvements on those. So that was always in our minds. Next chart, please. We felt the review was comprehensive. It involved about 900 of our people. It involved all levels of...
Is it 900 people, just I hate to interrupt you, but is it 900 people in toto or just for your area of review?
It was in my area, in this area of review.
I thank the gentleman.
It involved all levels. We had from engineering management all the way down through technicians. We wanted to have technicians involved for their viewpoints. We had all the disciplines involved. It did involve our NASA people and our contractor people, and the 900 did include both NASA, civil service, and contractor. We had participation with some members of the Air Force, and we had an active participation by members of the flight crew, which was important to us. In conclusion, we had several significant relevant findings, which we'll discuss in a few moments. We did find that our operating procedures do require correction in some areas, and that there are some processing practices we can be improved. We documented the results, and it was very in a large amount of volumes due to the amount of work and review that went on. What we tried to do to simplify that was to summarize it into a single document that would capture the essence of those other documents in the 6,000 pages. And that was submitted to the Commission along with a copy of all the background material in which they used then. Next chart, please. I'm going to move into the first area, the NSTS processing review. The job there, right after the accident, we impounded all the data, which included all the paper, any data that was associated with 51L processing. And what we did then was formulated into teams, which I'll show you just in a minute,
and went into the process of reviewing every bit of that documentation and the records, as well as interviews, to ascertain whether we had had any problems associated with any of these activities. We looked at how the flight hardware met with our mobile launch platform. We looked at Pad B, our launch complex Pad B, since this was the first use of it, to look for were there latent defects that could have been in our processing or in bringing that activation on board. We looked at the GSE that interface with the vehicle and the facilities that interface with the vehicles, looking for anomalies. We reviewed all our payload processing. We looked at the ICE team. We along with DOD, did look at the range support that does support the activities pre-launch at KSC, and analyzed all our problems and documented these findings. Next chart, please. These are the teams that we did put together and that did support this activity. As I mentioned, these started early on, and when the task force was formed, we went back and did a quick check to make sure that we did have a degree of independence. We didn't want to have people reviewing their own work, but we wanted people who were familiar with the work to be able to review it, and we found that to be the case. The outside members looking with us, such as the flight crew members, as well as the staff from the commission, gave us a feeling that we had a degree of independence, since we recognized that these were mainly KSC people looking at KSC work. And so we felt comfortable with that was the case, that we did have an objective look. And I'll now go into the major findings concerning the processing. Next chart, please. Our first major finding was that in conjunction with what had gone on the accident analysis team, we, looking at our activities, could find nothing that was that led up or contributed to the 51L accident. Now, I'd like to hesitate and stop there. There's one in the area of the SRB joint. The way the joint is put together, it is what we call a blind mate. That is, you can't see the internals once you're done with it. We do know that you can put the joint together correctly. We know this from test, and that you can have some joint sealing degradation. And the type of things that you can have, even though you have tested it and put it together properly, is you can find some minor, small contaminations. For example, when a pin goes in, as you saw in the earlier joint, there may be a metal sliver there in that, and there's no way to tell it. And the O-ring could be damaged, but yet still pass the seal test under some extreme conditions. And we know that we can have water in the joint, and we have no way to test for the water in the joint has been attested. When it was looked and weighed, even though the processing was done properly, as Mr. Thomas said earlier, it was felt that there was a low probability that there was any problem associated with the contributed by the processing. Next chart, please. One of the problems we did find was that our work control documentation system does require revision. This system has been in place and is a derivative of the system that was installed and instituted in early manned flight. What has happened to it is, due to the activity, it has become cumbersome, and to use a term it's not very user-friendly. This led to two problems. One was that people became sloppy in their practices, and this is an area that you can often say is just a discipline problem among our people. When we looked at it, we found that we had given them what we thought was a task in a system that was too cumbersome to really work with effectively. So what we're doing right now is we are in a process of looking at it. We have several teams bringing in all levels of the workforce, looking at how we can streamline it and make it what we would call more user-friendly. We're then also going to be emphasizing training on the importance of the system as well as how to use it, and we think those will lead to an improved system with more rigor in it and more discipline. We did not have a problem at the time with the paper system assuring that there were no contributors to the accident, because with the effort we put into it, we could find where the records were inadequate. By talking with people and working in that manner with special analysis, we knew we were all right. This is not what you want for a normal operation, and we intend to correct it. Next chart. Launch Complex 39B requires additional modification. This wasn't really a surprise to us. In fact, the complex turned out to be what we considered very good. However, we know we've got some hardening modifications to be made, and these are just where, in some cases, panels bulge due to negative pressure that we hadn't anticipated. We're going to have to put plugs and things like that. It's not a major item. The major thing we did find was that this freeze plan that we had instituted this time, which was also the first time been used, it was inadequate. And that led to the significant amounts of ice on the launch complex. This is going to be corrected, and it's underway right now, the definition of its correction. Next chart, please. One of the findings when you went through with the 900 people was that there were cases where we had some inefficiencies due to in our processing due to high workload. The high workload was contributed to a peaking of work that was somewhat more than we had anticipated. The 4 orbiters being processed was a new time for us, and when we got into it, it is not something due to the short-term nature of what we saw the problem that you could add people. I might say in most of our cases to get people fully up to qualification requires some 18 to 24 months, so you just can't go out and hire people, bring them in, and then have them be able to get the job done. So what we're looking at now is very carefully how we can approach our shifting and our manpower mix along with our contractors to assure that we have as much flexibility to unforeseen problems as we can in the future.
For clarity, will the gentleman hold at that point? On the top of that chart, you're referring to manpower limitations due to high workload created schedule difficulties. You're speaking now to the launching process itself.
That's correct, sir.
Thank you.
Next chart, please. This was not a problem since he had seen it before and understood the background. Our system is such that if you do something that is out of the ordinary, you should document it. And this was not documented, so therefore it went undetected through the system. There was no indication of a problem. It was reported during the post review of the data. But again, it was a very serious, in our view, situation of not following established procedures. What we're doing is, obviously, I think the seriousness of that is being stressed throughout the we did find a few test team errors that were caused by not following established procedures. Most of them were related to work control documentation systems, as we discussed earlier, the lack of being user-friendly. However, we did have some a couple very serious cases, and the most serious one was that we had a undetected slamming of the 17-inch disconnect. We know it's a critical problem. We worked, the reason it occurred, well, there are many reasons, but the fellow who slammed it is an experienced person who took the judgment onto himself that this was not a problem since he had seen it before and understood the background. Our system is such that if you do something that is out of the ordinary, you should document it. And this was not documented, so therefore it went undetected through the system. There was no indication of a problem. It was reported during the post-review of the data, but again, it was a very serious, in our view, situation of not following established procedures. What we're doing is, obviously, I think the seriousness of that is being stressed throughout the workforce. We're also going in to look at situations where have we been as rigorous in ferreting out places where human errors can occur on critical hardware and see if there aren't ways that we can preclude those. And we feel that with that we're going to reduce the propensity for this type of situation. Next chart, please. Mr. Holloway reported a test requirement system required revision. From their view of it, this is a similar type of finding that our team had looking at it from the KSC processing standpoint. And between the people in the program, there is work underway right now to make the correction to both of these findings. Next chart, please. The logistics system, orbiter logistics system supporting 51L was found to be inadequate, causing significant LRU cannibalization. I think this has been well reported. It was created by just a lack of parts and the level of degree of activity, and that we ended up out of some 300 parts required for the processing of 51L, that 45 of them had to be removed from another vehicle and placed into Challenger for use in 51L. Besides the manpower implications of that, there's an implication you just don't like to be working on vehicles, because anytime you get into a vehicle, it creates a potential safety hazard. So the program has been working, and Admiral Truly has initiated action already to try to beef up the spares program. Next chart. Additional analysis will be required to assess environmental effects upon launch capability. From the ground system standpoint, we had not developed adequate modeling, in my view, to know comprehensively all the problems that we might have through the launch complex. We had one cylinder, for example, that reacted slower. We had qualified it to 32 degrees, but when we looked at it, even though the ambient temperature was above 32 degrees, we hadn't run the modeling to find out exactly the temperatures there, and it was below freezing, and it reacted slower. It didn't create a problem, but it meant it was an area where we need to improve our information. Also, the instrumentation and the analysis of the temperatures all over the launch complex, we feel is going to have to be improved. And that, as it's pointed out, you just can't take a temperature measurement at one spot and have that be representative of the total complex. So we're looking at modeling techniques so that we can have an improved assessment ready. Ice debris was greater than predicted. There was much discussion on the pre-launch activity about the ice debris and where it would go. We did review that, and we found that when you reviewed the films post-launch, that the aspiration effects were greater than had been anticipated by the people who had pre-launch had participated in that discussion. There was, again, the ice did not create a problem, but it did show us that there is a need for improved modeling, if not for ice, but to look at the aspiration effects as it may affect all debris. So this is an area of reassessment. Next chart, please. That was the final finding we had that summarized all the 10 teams' activities as far as the STS processing. At this point, I would move into the flight readiness review process as it led to the launch decision. And the way we handled that, and due to the nature of it, it was one where I think that, in all fairness, that the Commission took the larger lead. And we worked off of data that the Commission had provided us. What we did was we analyzed the policies and procedures and found that essentially we were in compliance with that. Next chart, please. That was our first finding. And again, has been stated several times, the process itself, the structure of the process, is a consistent, fair process. Next chart, please. However, in all honesty, the flight readiness process did not address the critical SRB flight safety issues. And part of the rationale that you get is, I think, is in our determination was the lack of understanding of the full certification process. So therefore, when it came forward, even though the indications were coming forward, when it came down to the launch decision, there was not a clear understanding of the mechanism that was going on and operating at the low temperatures in the joint. And so consequently, we've got to review our whole system and how we lead up to that and decide what action should be taken. Next chart, please. It's another area I think that's been well documented. The communication during the launch decision process was inadequate, and that may be a poor choice of words on my part. What I was trying to portray is it was obvious in the after effect that there were people in Morton Thiokol at the engineering level whose concerns didn't reach those who said if they'd known of them, they might have taken other actions. I don't know, other than that, says that there has to be something wrong in the communication there, or improvements. Also, with regard to the ice debris in Rockwell, we had the senior officials of Rockwell believing they were talking on a flight safety issue, while the senior officials of NASA believed they were talking about an issue that was not safety of flight, but a refurbishment issue. And again, that type of communications it indicates there was a problem with the communication. Next chart, please. That was all I had on launch decision, in that there is a lot of review in that whole activity on there. But that was all we were asked to look at is a pre-launch team. The final area we have is the pre-launch security. In that activity, the assessment, again, initiated right after launch. And the review was done in conjunction not only with KSC, but aspects of local, state, and federal agencies to assure that all aspects of the security problem were looked at. And the next chart documents our major finding, and that there were no factors contributing to the 51L mishap were found as part of the security assessment. Next chart, please. However, we did say that based upon our look-see, or looking at that whole activity, that we wanted to reassess our national resource protection to assure, in light of all that we looked at, that we were doing a proper job in that, and this type of review is ongoing. And that's all I had, and that was the end of our findings, sir.
Okay.
Thank you.
I want to thank you, Mr. Utzman and your other colleagues for an excellent presentation and one of candor. And without objection, the chair would move that the testimony, the written testimony, the accompanying charts and graphics be incorporated as part of the committee's records at this point in the record? No objection, so ordered. In the pre-agreed discussion we had this morning as to our process this afternoon, Mr. Scheuer, the distinguished gentleman from New York, was proceeding upon a particular course of questioning, and we decided it would be apropos and workable to finish the testimony first of the distinguished representatives of NASA, which we've done at this point, and therefore the chair now defers to the gentleman from New York, Mr. Scheuer.
Thank you very much, Mr. Chairman. Dr. Fletcher, we were discussing this morning the remarkable body of evidence, the remarkable database that NASA achieved in a comparatively short period of about 6 weeks after the tragic accident, with the application of approximately $5 million and approximately 200 scientific and technical people. And I asked you if you could get for us this afternoon the resources and the personnel that were applied to addressing the problems that were enumerated in the February '83 warning, the July '85 warning, the August '85 warning, before launch. Do you have
Mr.
that?
Scheuer, as you know, we did look at that very hard during the lunch period, and I think we have some answers for you.
Good.
There was a study started after a flight readiness review when the joint problems were discussed quite extensively. The study was started in early 1984, and it looked at things like margin assessments, new designs, and new materials to be used in the joint. Additionally to that, at the Marshall Space Flight Center, there was some internal Marshall effort that looked at modeling of the joint, things like putty layup and et cetera that was ongoing. And also after each mission, when an incident occurred with the joint, there was some manpower and some dollars associated with doing a post-flight analysis. The total of this, with information that I could gather over the lunch hour, was in approximately $3.5 to $3.8 million. I don't know exactly how many people were involved, but I can supply that for the record.
Over how long a period of time?
This was over a period of...
This effort take place?
This was over a period of about 2 years.
Starting when?
In early 1984.
Mm-hmm.
The one thing that I have not been able to quantify that I think though is worth pointing out, which is that because the problem had been recognized earlier, but as the Commission's investigation quite clearly showed, we did not deal with it to the extent that we should. We did institute a design change into the joint, the metal for the joint itself that has been referred to as a capture tang, that was designed to reduce the joint rotation that has been discussed here today. That capture tang, that metal in that capture tang was designed into the design for the filament wound case. That's a new version of the solid rocket motor that is designed and is under development to be used out at Vandenberg Air Force Base for West Coast launches. And in the summer of last year, the decision was made...
Summer of '85.
The summer of '85, yes, sir. The decision was made to, in the case billets, the raw billets that were being produced to later be machined, that enough metal would be delivered. The design of those raw billets would have enough metal so that the steel cases could also have such a capture tang. I don't have a dollar number to put on what went into that particular design change. So I guess I would, in summary, to answer your question, it was less than $5 million, $3.5 to $3.7 million over a period of the last 2 years, plus the cost of that capture tang, and I can get that, but I don't have it now.
Well, now, as of August of last summer, in the third of these 3 early warning signals that all was not well, the recommendation was made in this final briefing to the NASA people, to Michael Weeks and others. The recommendation was made that efforts need to be continue at an accelerated pace to eliminate seal erosion, and that additional tests need to be conducted for establishing margins of safety for eroded O-rings. Now, this was 1.5 years into that 2-year effort you're talking about. So apparently it was quite clear, as of 18 months into that period, that there was vast additional data that had to be accrued before launch should be effective. Let me ask you, do you agree with the statement made in this Presidential Commission report on page 148 that, and I refer to item 5 in the second column, the O-ring erosion history presented to Level 1 at NASA headquarters in August 1985, the briefing that I just referred to, was sufficiently detailed to require corrective action prior to the next flight. Do you agree with that?
I accept that. I'm sure that it is correct. It was a conclusion of the commission. I think it is quite clear in hindsight that the O-ring problem should have been dealt properly with, and that's a point that you made earlier, and I'm very glad that you did, is that the fact that this problem was missed was not only a problem at the Marshall Space Flight Center, but also at NASA headquarters. The signs were there. The commission, in retrospect, the commission and our task force and this tremendous amount of effort that we've put on it, which is the nature of accident investigations, has shown that improper attention to this crucial problem was given, and it was not limited to the people at the Marshall Space Flight Center.
Yeah. Mr. Chairman, would we have in the audience a gentleman, the Deputy Associate Administrator for Flight of NASA, Mr. Weeks, and I wonder if we could ask him to come to the witness table.
I believe Mr. Weeks is here. If we may, Mr. Fletcher, or Dr. Fletcher, we'd like to have him come to the table and for some questioning.
Yeah.
Mr. Chairman, this is Mr. Michael Weeks. He was the Deputy Administrator at the time of the accident.
Deputy Administrator for Flight.
You want to welcome Mr.
I'm sorry, Deputy Associate Administrator for Manned Space, or for the SDS.
Yes.
Mr.
Right.
Weeks, go ahead, Mr.
Mr. Weeks, in February '83, you signed a waiver of the fail-safe requirement for the joints, correct?
That's correct.
Right. And in July '85, you were alerted to the problem of the joints when Irving Davids wrote a memo, which you were copied.
Mm-hmm.
Right?
That's correct.
Okay. Then in August '85, you were present at a briefing about the repeated failure of the O-rings, in which you were urged, I mean the collective group, were urged to make efforts to continue at an accelerated pace, efforts to eliminate the seal erosion, and to conduct additional tests for establishing margin of safety for O-rings, okay? Right? Now, what I'd like to know, at that point in time, in August of 1985, with a launch date for Challenger staring you in the face not many months hence, but with these critical warnings in your possession, what kind of resources did you spend to address yourself to the problems that this memo urged you to address at an accelerated pace? How many people, how many dollars, what did you learn, and what did you do about it?
As Admiral Truly spoke to you, I think I should
Mr. Weeks, I'm asking you four very simple questions
I understand that.
which demand a factual answer.
The effort after that August meeting that we had, which was quite an important one.
What was important, the meeting or the effort?
No, the effort and the problem of the erosion of the secondary O-ring.
Well, we know the problem was important. What we want to know is what did you do about the problem when you were warned about it for the third successive time? What happened after that August meeting?
The key items that happened after that was the studies that Admiral Truly's already spoke to.
And what did you learn from those studies?
That there was essentially, as we have found now, it's about a 2-year program.
Essentially what?
It's about a 2-year program to bring the capture tang and any changes into that joint to eliminate all of those problems that Mr. John Thomas talked about. Now,
I don't understand that. It was a 6 weeks program that just took place to put together the database to tell you under no circumstances should this launch take place. Now, what I want to know,
wait a minute.
The question that all of us want to know is...
under no circumstances, I believe, really, Mr. Scheuer, you should... Sure, excuse me. The conclusion of that briefing given to us on August the 19th was it is safe to continue flying the existing design as long as joints are leak tested with 200 psi stabilization pressure and are free of contamination in the seal areas and meet the O-ring squeeze requirements. Now, Marshall did proceed with a number of hardware things that were put into the filament wound case qual test motor. They were basically 3. In addition to all this study effort, there were 3 changes made in the qual motor of the filament wound case because that was coming along and was an opportunity to put them in. And so we inserted into the qual motor program the fixes that I will now relate. There were basically 3 of them. As Admiral Truly said, in July of '85, we ordered those 72 forgings with the extra material so that we can now, for the fix that we're going to have to do, provide the capture tang to stop the rotation.
Let me
and
ask
that
you this.
decision...
Let me cut you
well,
short.
I really think that to get the 3 things that were quite fundamental as a result of that...
The gentlemen will both suspend. There's a bit of excitement in the air because we're trying to get to certain facts. I think Mr. Scheuer had asked you an initial question which you really didn't answer. But if I could impose upon the distinguished gentleman from New York to allow the witness to make his observations, then let's go back then and restructure our questions. Is that satisfactory?
Very good.
So we'll give you the courtesy of giving your...
All right, I appreciate that.
Thank you. Go ahead.
So these, in addition to those studies that Admiral Truly spoke to, there were these 3 things that we put into the hardware. The 72 forgings were ordered because we knew the rotation problem was serious, and we had changed the design in the filament wound case so that it did have a capture tank. That decision of proceeding with those 72 forgings is now saving us 6 to 9 months in the implementation program that Mr. John Thomas is heading up, that would have delayed us more had we not made that decision. These forgings, in fact, are already at ROAR in San Diego.
Can the gentleman, just for clarity, explain to the committee what he means by forgings and where the forgings are located?
Okay. The solid rocket motor is composed of a lot of spun forgings that are 146 inches in diameter and 12 feet long. I think Mr. Lee showed that. It takes 2 of those forgings, properly machined, to make up a single segment that can then be poured with propellant with, I think, as you, Mr. Rowe, spoke to, of the joint that is covered over that is the same sort of joint. Okay. And so that's what those forgings are. They're spun. They're done by the Lattice Corporation up in Milwaukee. And then they are shipped to ROAR in California for machining. And already, with that decision that we made to move out on those forgings, we've gained ourselves 6 to 9 months that we would otherwise have due to this terrible accident. And we changed 2 of the 3 case joints as a research project, changing the O-rings in 2 of the 3. In this qual motor, which was for the filament wound case, and that was to improve the sealing. And the last change of the hardware that was put in the qual motor into the filament wound case qual motor, and that stops the rotation, and that one is down the throat area. The basic idea of the capture tang, which is a very likely candidate for the way we will fix the joint for the final, for when we get flying, is a capture tang that forbids the rotation to exceed more than about 19 thousandths of an inch. And that, in addition to the study effort, are very positive things that were done by Marshall and Thiokol to move forward in this area of improving the O-ring erosion, which occurred many times during the past 2 years.
All right. Now, if we can get back to our continuity, Mr. Weeks, we thank you for your explanation, but I believe what Mr. Scheuer is about to do is to evolve a set of questions that really are not looking for long technical explanations, and I mean no effrontery to your expertise, but what actually happened? What did we do? And that's what
that's...
Can I rephrase my questions, Mr.
Yes.
Chairman?
Sure. Let's start again.
Let me rephrase the questions, because maybe I wasn't sufficiently clear. Following the meeting on August 19th, where you were urged to make efforts to continue at an accelerated pace the elimination of the seal erosion, where you were urged to make additional tests for establishing margins of safety for O-rings, conditions which apparently impelled the Commission to write that the O-ring history presented at Level 1 at NASA headquarters in August '85 was sufficiently detailed to require corrective action prior to the next flight. Now, having been urged to make an accelerated research and development effort to eliminate seal erosion and to establish margin for safety for eroded C-rings, for eroded O-rings, what did you do?
The accelerated program was very clear in those 3 things I just told you that were put into the qual motor test for the filament wound case, which were genuine improvements to reduce the probability of erosion occurring in those joints.
Will the gentleman yield at that point for a point of clarity?
Yes.
Did you not say two things, as I understand it, when the discussion took place, that the results of the review at the discussion indicated that if you were to correct the system, that it would take 2 years?
In the time period that we were doing that, the best estimate we had for a capture tank design configuration was about two years.
All right, all I'm simply trying to get at is just to elucidate your specific statements and facts you made, either they're correct or not. Therefore, do I assume from that, if the gentleman will indulge me further, do I assume from that if I'm talking to you and we're deciding we have a problem, and you say, well, we do have a problem, we've discussed it, well, okay, now I'm concerned about that. What I want to do is get that totally corrected so we do not have any more problem. In order to pursue that course of action, how long approximately do you think it will take? And then you respond to me, you say, well, for my best judgment, it'll take approximately 2 years. Is that an accurate observations of your point? Okay.
Yes, sir.
Can I take it from there, Mr.
Yes, you can,
Chairman?
of course. I just want to establish that.
There was a life-threatening condition there, which the commission said should have been corrected prior to the next flight, okay? Do you disagree with this conclusion? Do you feel that that research should have gone on over the 2 years that you suggest it would take while 25 or 30 additional space flights were being carried out? Should those two things have happened simultaneously, concurrently?
Well, Mr. Scher, it is much easier to look at this thing with 20/20 hindsight, but I still remind you of the following things that we knew at that time. When the briefing was presented to us on August 19th of '85, as you will look in the briefing that was provided to the Commission on February the 10th, there was no temperature data presented that showed that the resiliency was such a critical factor. It wasn't until after the disaster of 51L that I actually saw the resiliency data that showed that Viton, which is the O-ring material we've been using, is so slow to recover at very low temperatures. That was not, sir, that was not brought out in that time.
We are engaged here in, let us admit, an effort at Monday morning quarterbacking. Should we be doing something else? Should we not all be trying to find out what the problems were and what should have happened that didn't happen that produced that awful accident? Of course we should. There's no point in debating that. Now, what I'm suggesting is that you had in your possession, I mean the decision makers, the corporate decision makers at NASA headquarters, 3 separate warnings that should have given you notice that this launch shouldn't take place until these problems that were identified were solved. That's what the commission said. Let me read it to you over again. I read it to you once before. I'll read it again. The O-ring erosion history presented to Level 1 at NASA headquarters in August of 1985, at the meeting at which you were present, was sufficiently detailed to require corrective action prior to the next flight. Now, do you disagree with that?
In 20/20 hindsight, I totally agree with you, sir.
Okay. Now, we're looking at this from 20/20 hindsight. We're all trying to learn some lessons. We're all trying to learn some lessons. And frankly, there may be some lessons in this whole tragic series of events that Congress could learn from. Maybe we didn't do as much as we could have in funding and encouragement and oversight. There's probably enough blame to go around for everybody. So there are no super people here, no super men and women who are pointing the blame at anybody else. We're all in this together. We're all trying to learn how to avoid this awful catastrophe in the future and move forward successfully to retake America's supreme place in space.
I can't disagree with you, sir.
Pardon?
I cannot disagree with you that it would be extremely wise if we could have seen to have done this $5 million effort that took 6
Well,
weeks.
what I'm asking you is
in
what effort
September of '85.
Right, what effort
I
did
wish I
take
could
place?
relive that history and do it.
That may be enough for my purposes.
Will the gentleman yield? I want to get another point on
Let
the
me
record.
ask this, let me ask one more question.
Well, there's a point of clarity that's not clear, Jim.
I yield to my chairman.
The gentleman in making his earlier testimony, we solidified the point of view of the 2 years which we agreed on. You made another statement which I think is important. The second statement you made that it was determined in the course of that discussion, as I recall what you said, that even though the severity of the issue was understood, that it was decided it wasn't that severe that you could not proceed with additional launchings or whatever that meant, even though you would be doing some redesigning as you went along. Did I not understand you to make that comment?
That's correct, and I think that the statement of the conclusion of the briefing is quite significant in that it is safe to continue flying the existing design as long as we did those 3 things that are in that
Now, if the
in that
gentleman,
briefing.
if the gentleman would expand upon that further, therefore there were a group of people, whomever they were, that participated at this particular meeting, reviewed these facts that were available, and determined that they determined 2 things, according to your testimony. One, they determined that if everything, they had their druthers or whatever the case may be, it would take 2 years in their judgment to be able to correct that. But in spite of that decision, they made a second judgment, and the second judgment, well, we can continue to fly. We'll start the mechanisms going to get this corrected, but we can continue to fly until we get that done. Isn't that the decision that was made?
That was correct.
According to what you're saying?
That is correct.
Therefore, some people who were at that specific meeting had to be the people who made that specific decision.
That's
Is that
correct.
fair commentary?
That's
Do we
correct.
have a list of the people who
I
participated?
have it right here.
Would you submit the list for the record, please?
Sure can. I have it in my briefcase, but we'll...
Was Jess Moore at that meeting?
No, sir. Mr. Moore was...
Well, let me finish the first parliamentary issue first, Mr. Scheuer, if I may. Therefore, the gentleman would submit for the record the list of the names of the people that participated in that meeting. The chair recognizes the gentleman from New York.
Point of clarification.
Yes,
I
sir.
thought we were operating under the 5-minute
No,
rule
we-
here, and it's been a half an hour, and there have been a lot of other members that have been very patiently waiting.
Well, that's probably the chair's fault, because this afternoon the chair had decided, because of specific questions where people have been waiting all day, that we'd give people a little more latitude. But it's not the intention of the chairman to turn anybody off, and we'll give the gentleman the same courtesies in return. The gentleman from New York.
Thank you. Mr. Weeks, you were telling us about Jess Moore's presence.
Yes, sir.
Was he at the meeting?
No, sir. He had planned to go to the meeting, but he was, some other prior pressure caused him to go to a meeting. But I did brief Mr. Moore that evening, as we were wont to do in the early morning and the evening. I briefed him on the results of that and told him about that briefing and showed him the briefing. And as we left that evening, I said I was still not quite satisfied, and I wanted to call someone that I had great trust in, and I so did do that to Mr. George Hardy of the Marshall Spaceflight Center, who had headed up the SRB for many years and then moved up to be deputy engineering. And I had great faith in his judgment, and I asked him, how bad is it? And he allayed my fears, and I think it came from the fact that we did do a test that showed that we had a factor of safety of 4 on the 032 erosion that occurred.
Isn't it clear that we really didn't know enough at that time to really come to any conclusions about a factor of safety, except to know we had life-threatening conditions to which we ought to have achieved answers before we went ahead? Isn't this what the report is all about? That corrective action was required prior to the next flight. And the fact was that you have learned more in this 6 weeks of collective effort through the expenditure of $5 million and the application of 200 trained scientific and technical minds than you knew through that entire 2-year effort up to the date of launch. Isn't that true? You really didn't know what the problem was with the seal erosion and with the margins of safety for eroded O-rings as of the time that that launch took place. Isn't that true?
I essentially agree with you, sir. That joint with the putty problem, with the rotation problem, with the temperature problem, are all very complicated, and I agree that the effort after was extremely effective, and we learned immensely after the accident.
Wouldn't you say, with the benefit of hindsight, that following the warnings of that August 19th meeting to accelerate the pace of research into seal erosion and to accelerate the tests for establishing margins of safety for eroded A-rings, that the simple, clear message of that briefing was, do your homework before going ahead with another launch, because you have life-threatening conditions that must be faced and for which solutions must be found. Wasn't that the clear meaning of that briefing on August 19th?
Yes, sir.
Why wasn't that done? Your boss knew about it. You reported to him that evening.
Mm-hmm.
Looking at it in hindsight, what have we got to learn? Why didn't you and Mr. Moore and the other decision makers follow up on those recommendations and either do the work in the next 6 weeks, which would have been a replica of what you did in the last 6 weeks or so, or why didn't you postpone the launch until you had done your homework?
If we had known that clearly, how crisply to do this problem, we certainly should have done it.
I'll be happy to use.
Yes, he was just finishing, but go
ahead. This matter and not hammer on something that's not redoable. I think that the Commission's report makes a rather cogent statement that reflects directly on what the gentleman from New York is pursuing. It says if the decision makers had known all the facts, it is highly unlikely that they would have decided to launch 51L on January 28, 1986. And I think that that's what we're hearing from the witnesses. And I think that's what we're trying to determine, is how to avoid repeating this problem again, and I'm not sure that it would be productive to pursue it further.
The chair has allowed this discussion to go this far simply because of the point of view that I believe that it's a subliminal issue. Mr. Weeks, you become quite, well-known, if you like, throughout the nation because of the position decision you made. What Mr. Shore wants to do, if the gentleman from California understands, is just to get on the record the sequence of events that took place. And I think you've done a good job in making that presentation. Yes, I do, of course.
I think this has been very helpful, and I wish to express my feeling that Mr. Weeks has been forthcoming in his testimony. It took a little time, but he's given us what seems to be an answer view. They should have known a lot more before they proceeded. In hindsight, any other conclusion would be difficult to come to. There's been a lot of finger-pointing here at Marshall, but I think it's fair to say that Central Headquarters also has played a major role in this, and I think that we shouldn't forget this as we proceed with these hearings, Mr. Chairman. I hope we'll have a chance to ask Mr. Weeks to come back. He's been very helpful today, and I appreciate his forthcoming testimony, and I hope we'll have the chance to ask him some further questions.
I thank the gentleman from New York.
Can I yield to my colleague, Mr. Nelson?
If I could just chair the meeting, then I will let you yield. I would like to make it clear to all of our members that there's no one's going to be, we seem to have, I don't know, maybe it's the Ides of June, seems to be a little testiness today unnecessarily. I think the chair has been overabundantly generous to every member on any particular issue, in any particular area that they chose to make their points, to be able to make them. And I intend to see that the hearing continues under that decorum and under that direction, and no one will be precluded from their point and their opportunity. I want to make that point abundantly clear. I want to make another point clear, I think, that ought to be said at this point in the stage of the hearings. We have work yet to do, and very important work to do. And I think we've successfully come to a point where, as far as the obligations and the responsibilities of the Commission, they have made a report. We are now very, very carefully and very legitimately following up on point to point. Everybody practically at this table, one time or another, has said there's plenty of blame to go around. There is, for everybody. That's not our mission. Our mission is not to neither crucify nor kill. That is not our mission. Our fundamental mission is to understand what happened, why it happened, and how we correct it, and what policies we set for the nation. That is the purpose of this hearing. Now, there'll be some blood and some scar tissue, I'm sure, when we're done. But it's going to be fair, and it's going to be honest, and it's going to be just. And I think that's the direction which we shall have been continuing. That's the direction we will continue. Now, having said that, I will now yield to the distinguished gentleman from Florida, Mr. William Nelson, because he has a series of questions he would like to ask.
Okay.
The chair recognizes the distinguished gentleman from Florida.
And I appreciate it. The reason I'd asked the gentleman from New York to yield was that I just wanted to follow up just with a question or two to Mr. Weeks. After this famous meeting that occurred in August, did you or anyone else issue instructions to Marshall or to Kennedy to take care of those three problems that were noted in the Thiokol report in that famous meeting?
Yes, Mr. Paul Herr sent a memo to Marshall following up on the August 19th meeting, and I can't remember the date of Mr. Herr's memo.
All right, may we have a copy of that, please?
We will find for you. Yes, it's available.
All right, send that to me personally, please, and to Mr. Scheuer. All right, now, Mr. Weeks, what specifically does it mean in the Thiokol report when it says meet O-ring squeeze requirements?
The basic limit, Mr. Nelson, on the minimum squeeze is 7.5% of the diameter of the O-ring itself. So that means roughly that you shall not have a squeeze less than 20 thousandths approximately on the 280 thousandths O-ring.
Were those requirements met on 51L?
I believe so.
Were they
in fact,
met?
I think John Thomas could probably answer that, but I believe it was in the vicinity of 035.
Mr. Thomas?
Yes, sir, that is correct. They were met.
Okay. Now, was there concern about excess squeeze or maximum squeeze?
Yes, I believe so, but I believe, as I understood the problem then, and I guess as I do now, that the more serious one is when you get the rotation with the minimum squeeze, which then, if you don't have good resilience, doesn't fill up the gap and contain the gases. But I believe there is a concern at the highway, but I don't believe it's the crucially serious one.
All right. Were these squeeze requirements met on all of the flights after the 19th of August, 85?
I can't be totally authoritative, but I've never heard anyone say that they did not.
Okay. Mr. Thomas, do you have any information with regard to that? Okay. Supply that for us, Mr. Weeks, if you will. Okay, Mr. Chairman, I want to now pick up on the question that I asked in Dr. Fletcher's absence yesterday morning. I asked Admiral Truly, and he said that Mr. Lee would supply the answer today, so if Mr. Lee would come up.
Mr. Lee, please.
I further privately discussed this with Dr. Fletcher, and it gets into the question of the testing and analysis requirements on the whole SRB, not just the joint, the whole SRB. Under the design specs, it was to go down on natural environment down to 31 degrees, and under induced environment, it was to go down to 21 degrees. And there was supposed to be testing and analysis on this. And the reason this was raised was when you briefed this committee down at the Kennedy Space Center on Friday, you told us that you had no evidence that such testing and analysis in fact was done. Would you restate that for the record as to what you told us Friday?
Yes, sir. Mr. Nelson, with your permission, you stated that the lower limit on the induced temperature was 21. It's 26, I believe. 26 degrees Fahrenheit.
No, sir, not in these documents. It says 21 in here, but be that as it may,
well,
let's go on.
It is, in fact, 26 degrees. The finding that the Commission Production and Development...
well, let's just clarify that. I have a document here, as long as we're going to get specific. NASA Technical Memorandum. Is this the cover page for it? Okay. Dated November the 19th, 1973. Marshall Space Flight Center. Gives temperature, degrees Fahrenheit, talks about the aft attachment, talks temperature in degrees Fahrenheit, hot max of 96, cold minimum of 21.
I'm not familiar with that particular document. I was referring to the overall system specification that is from the shuttle overall specification, which is imposed on our element contractors, and that is, in fact, 26 to 120 degrees Fahrenheit induced.
All right, it's a minor point. We'll clarify it later on between exchange of paper.
Mr.
But,
Nelson, did you say 1973?
That's correct. That's the date.
I'm not sure, but that could have been before Morton Thiokol was selected. I think we ought to check the date, but I believe that was an early spec which may have been changed by the time we had the solid rocket contractor on board.
All right, we'll check it. Go ahead.
All right, sir. Mr. Sutter's commission team, which I supported, found that the requirements for that specification were satisfied by the Morton Thiokol Company through either qualification testing, analysis, or inspection, or acceptance testing. Now, in the case of the seal joint itself, for the certification, the acceptance of the certification of that joint, it was specified to be done by analysis. That was proposed by the Morton Thiokol Company, and Marshall Space Flight Center accepted that by analysis. As I stated this morning, the interpretation of that induced requirement by Morton Thiokol was not associated with vertical flight, but more as a storage temperature. So given that situation, their limitation or band or range of temperatures for qualification to them was that associated with the mean bulk temperature, which they believed encompassed all environmental requirements for the motor from a qualification standpoint, was 40 degrees to 90 degrees. Now, that's what they did, in fact, state to our team when we reviewed this. It is my interpretation, and the writer of the specification, the keeper of that spec at JSC, and the project office at Solid Rocket Booster Project Office at Marshall, that the intent was to be 26 to 120 through vertical flight. Now, that makes a difference in the way you go about satisfying or certifying that. In any event, the certification method was by analysis, and the data presented to certify that environment to the government, if you will, was a mill spec on the O-ring which states clearly that the O-ring can be operated between the temperatures of -30 and 500. Now, the interpreters of the meeting of that certification on the part of the government was that the O-ring was the critical part. It did, in fact, was usable through those ranges. Now, in hindsight, it is determined by Mr. Sutter's team that the proper imposition, if you will, for the method of certification probably should have been by test, which it wasn't, in light of the accident, and the stated satisfaction, if you will, by analysis of using only the O-ring spec was inadequate or improper. So the issue is around the interpretation of the specification, and in light of the accident, we should have gone through a full-scale qualification through all those environments. So there's a misinterpretation and probably a lack of imposition, if you will, or inadequate imposition of the method of qualification. And that was, in fact, the issue that our team came out with, is that under criticality, items of this type of criticality, that it should be the method of certification and qualification should be further scrutinized and ensured that they do in fact go through the full qualification range. That was the intent of the whole thing, not to impose or imply that the Morton Thiokol did not satisfy their contractual requirements.
Friday, you showed us the same chart that you showed us today, which said significant findings. The first one is qualification not accomplished to required spec limits.
That's right.
You explained that Friday at the Kennedy Space Center, and you said that the adequate testing and analysis had not been done, and when I asked why, you said nobody knows why.
I'm sorry, I don't remember giving exactly that answer. I believe in answer to the question, I stated that the people who were there at the time in the development program back in the late 70s, who were in fact required to interpret the adequacy of that certification, who actually signed off on the certification and qualification, are no longer with us. I believe that was the intent of my answer, as opposed to no one knew.
Okay, so what you're saying today is that analysis was required, which in fact the documentation shows, for both the natural environment and the induced environment. And you're saying that the interpretation of what analysis should be was that it would go down to 26 degrees in a stored condition. Is that correct?
Yes, sir.
But that's not what the design specs call for. And I read from 3.22117.2, which is on a document entitled Space Shuttle Flight and Ground System Specification, dated September the 30th, 1983, from the Johnson Space Center. And let me read for you. Induced environment. Each element shall be capable of withstanding the induced environment imposed during transportation, ground operations, handling, and flight operations. Flight operations. One verification completion notice is done just before STS-1, and the second one is done just before STS-5. So the obvious question is, why were they signed?
Yeah. Are the government signatures?
Yes, there's a whole raft of signatures here.
Well, again, the basis for that certification was, in fact, what was interpreted to be the completion of the analysis, and that was the O-ring itself was, in fact, a mil-spec designed to go from -30 to 500 degrees Fahrenheit.
Okay, now how could they come to an interpretation that that meant only for storage?
Yeah, I don't know that, Congressman. I only know that the people on my team who evaluate it interpret the same way you do. The writer of the document interprets it the same way you do, and I think the project office does. I cannot answer for why the Martin Thiokol did not interpret it that same way during the development program.
Well, first of all, we have 2 verification completion notices that have been signed. This induced environment is in fact one of the verification requirements completed and signed off. One verification completion notice is done just before STS-1, and the second one is done just before STS-5. So the obvious question is, why were they signed?
Yeah. Are the government signatures?
Yes, there's a whole raft of signatures here.
Well, again, the basis for that certification was, in fact, what was interpreted to be the completion of the analysis, and that was the O-ring itself was, in fact, a mil-spec designed to go from -30 to 500 degrees Fahrenheit.
Well, you're talking about the that doesn't answer the question.
Well,
the answer to the question, what you're saying is you don't know why these were signed because the analysis was not done according to the design criteria.
No, sir. I'm saying that it was established that the certification would be completed by analysis. Also stating that the analysis in this case was the recognition that the O-ring itself was good to be used between the temperatures of -30 and 500 degrees. That's the documentation which I have seen that was used to say this is in fact certified for those temperatures.
If the design specs say otherwise, then who made that determination? That they were going to test or analyze, in this case, analysis, to a different standard than in the specs?
Well, the determination to certify it by analysis was proposed by Thiokol and approved by NASA. The method for that analysis happened to be the mil-spec, and the mil-spec calls for a temperature range which encompasses the 26 degrees to 120 degrees.
Will the gentleman yield for clarity, please?
Certainly.
The question that's being asked, and the distinguished gentleman, Mr. Lee, comes back and says they decided that we would do an analysis, and then we have been carrying on about 20 minutes of dialogue relating thereto. But the fundamental question is, who decided that we would use the analyses approach? Who made that decision?
That was approved at the project office level within Marshall and the program or project office level at Martin Thiokol.
Now think what you said. It was approved by.
Yes,
and
sir.
I asked you, who made the decision?
Oh.
Did it come from Thiokol? Did it come from NASA? Was it from Thiokol? NASA corroborated?
I'm sorry. It was proposed by Thiokol as a company.
So are we saying for the record that that initial decision to use the analyses approach was suggested or recommended by Thiokol,
Yes,
but
sir.
however, after review, the NASA authorities, whoever had the jurisdiction, approved that approach?
Yes, sir. That's
Is
true.
that correct for
That's
the record?
correct. Yes, sir.
The gentleman from Florida will proceed.
All right, thank you, Mr. Chairman. I think another hindrance in our conversation here, and, you know, isn't that interesting that, you know, it's just a human foible of communication, and that in large part, Dr. Fletcher, is what the Rogers Commission has pointed out. It's a a mistake in communication that occurred in so many areas. So in trying to hone in the clarity of our communication, let's make sure. You're talking about that an analysis was determined on the basis of the O-ring itself. But
Yes,
that's
sir.
not what the design requirement. The design requirement is for everything on the SRB, not just the O-ring. If in fact this document that I have is an accurate one here, entitled from Johnson Space Center, Space Shuttle Flight and Ground System Specification, Level 2 Program Definition and Requirements, September 30th, 1983. And it clearly says what are the design environments, the natural environment as well as the induced environment. And it clearly includes flight operations. And it says each element. It doesn't say just the O-rings. So when you get into your analysis and then you start signing off on these verification completions, and Mr. Lee, I'm not picking on you. You all have done an excellent job. By the way, Dr. Fletcher, I wanted to compliment you. You know, what we learned on Friday and subsequent my private conversations with Chairman Rogers, he thought that your NASA investigatory team did an excellent job. The ones that we've heard the reports from each of the people today. And basically, you know, what you all concluded and reported here today and reported to us last Friday is in fact the same facts that the Commission reported. But now we find a specific question here of why were these verifications signed off on for a requirement in the design specs? Does anybody have any clues? Anybody?
Mr. Nelson, of course, this happened when I wasn't here, but I'm sure you're aware that there's a difference between a component requirement, which is the O-ring, which had the mil spec on it, and which was accepted as a analysis, and the system of which it's a part, which includes the O-ring and the groove into which it fit and the whole seal. And I think what we're seeing here is we accepted the mil-spec on the O-ring, but we didn't have adequate verification that tests were made on the whole system, which is the seal.
Including
and
the
it
putty.
just plain fell through the cracks.
Including the putty.
Yes, sir.
Putty wasn't tested down to 26 degrees, was it?
That's true. Thank you.
Well, I'll just yield to my friend from California.
Gentleman from California.
I appreciate that. I don't, my line of questioning doesn't necessarily follow on the gentleman from Florida, although that was...
You don't want to break my train of thought, do you?
I don't, and so let me yield back. That was one of the questions I had, but he's pursuing it adequately, and may I ask the chairman to allow him to go ahead and complete?
We'll be next. We'll talk. Go ahead, gentleman from Florida.
Okay. How, anyone, Admiral Truly, Dr. Fletcher, how do we go about determining whether or not such analysis was ever made? Do we know, in fact, today that the analysis was never made down to 26 degrees?
I think I can answer that. Because it was a concern to our group, when we found that particular situation around the joint, we did, in fact, review or attempt to find all documentation, all analyses, all tests to help support that. And we could not find any analyses other than that which has been stated relative to the mil-spec of the O-ring. It is, and that is, again, Mr. Nelson, one of the reasons that we as our team brought this, identified this as a finding, because we believed it was in fact inadequate in the system.
Okay, assuming that that is the case, that y'all do not uncover this analysis, documentation of this analysis, assuming that it does not in fact exist, then what can we do to crawl inside the minds of these people, some, looks like about 24 signatures on this page before STS-1 in March of '81, and again in November of '82 before STS-5. What can we do to crawl inside their heads?
I guess I'm the experienced manager in terms of team motivation, but basically, it doesn't matter, Mr. Nelson, how many signatures are on the document, as long as at least one of them has understood the problem, feels responsibility for pursuing the problem in the depth that's necessary, which, as I indicated, it was a systems problem, not just a component problem. We need to tighten up and make sure there are at least one plus a checkup on that person to make sure that it is done satisfactorily.
Okay, if you would do that, and if you'd report back to us, I would appreciate it. And while you're doing that, Dr. Fletcher, there are some other people that you could perchance go to for additional information. And that is, we understand that a thorough review was made by a group of experts headed by Dr. Walt Williams. And that, so you had on these design specs, you had a lot of people overseeing it. You had Thiokol, you had Marshall, you had this outside group of experts, and the Aerospace Safety Advisory Panel. So let's see if we can crawl inside their heads as well and see if we can get any clarification on it. Okay. Mr. Chairman, if I may continue.
Yes. Are you on the same vein? Let me give you a break and let's hear a little bit from
You'd
our
like
friend.
to give me a break, Mr. Chairman, that's fine.
You're going to be here for a while and so am I. So
Indeed.
Let's defer for the moment to the distinguished gentleman from California, Mr. Packard.
Thank you, Mr. Chairman. I want to go back to the O-ring problem and ask some specific questions as to where we go from here. And I need a little background before we do. In your judgment, as you've reviewed the Commission's report and as you've reviewed your own team's research, do you feel that cold weather alone, devoid of water and ice in the joint, would have caused the accident? Without water and ice in the O-ring joint, but still having the cold weather, in your judgment, would there have been an accident?
I think the cold weather was probably the most significant influence in the 4 or 5 that John Thomas described today. It took us over the edge. That's my own judgment.
The cold weather, not the ice.
That's correct.
Of course, the cold weather caused the ice, but do you think that was, in other words, you feel
the effect of the cold weather on the O-ring?
The temperature at 28 degrees or 29 degrees was more critical than the fact that it was ice.
That would certainly be my judgment.
How many O-rings are there on the entire SRB? O-ring joints, excuse me. Two
per joint, 6 field joints?
I don't mean O-rings, I mean joints. How many joints are there on one of the SRBs?
Yeah, there's 6 field joints.
6 total joints, I'm asking now, both factory and field.
There are 14 total, I believe.
Well, all right, let me ask the question again. It's not critical the number. The factory joints, has there been any problem with the factory joints in the history of the equipment and our launch system? Have we had any history of problems as we've returned and recovered and refurbished? Have we looked at the factory joints
Yes, sir. They've
And
been looked at.
has there
None
been-
of any.
And
of
as
this-
we've looked at those factory joints, have they shown any deterioration of the O-rings?
Let me check and make sure we've got no evidence of any erosion and heat. I believe the answer is no, we have not. But in terms of, being precise on that and make sure there's absolutely none on any factory joint, I'd like to be able to come back and confirm that there are none. I believe that to be the case.
So it's anticipated if you find no history of deterioration of factory O-ring joints, then you would not anticipate any redesign of those particular factory joints.
Well, wait a minute. Let me add a point I think is necessary for clarity right at this point. The question, so that we all understand what we're talking about, as I understand it, if the gentleman would yield, is that the configuration of the factory joints is identical with the O-ring configurations over, as is the field joint. Is
my
that a
understanding.
correct assumption?
Yes, sir.
All right, so therefore, just for clarity, I want to get,
that's my
therefore, what
question.
we're saying is that regardless of what the issues are involved, factory or field, it's identically the same mechanism, same structure.
Is that correct, Admiral Truly? Because that is, I've gone on that assumption.
Yes. The
Insulation.
That's right.
Admiral?
The configuration of the O-rings, which was your question, is identical between factory and field joints. There is a design difference, however, which because the factory joints are covered with insulation at the factory with propellant poured over that insulation, and that is the single difference.
Well, if the gentleman from California would yield, one of the issues that emerged into the discussion today that related to where that extra smoke came from the exchange of views that the interpretation, I believe, Mr. Thomas, that in testing further, I believe it was Mr. Thomas, I don't remember, that it was the insulation that added to that issue. Is that a correct remembrance? That the insulation is above and beyond the oil and the grease and whatever, and the organic material, viz. The rubber whatever in the O-ring, was part of the smoke. But in addition, what created the more volumetric amount of smoke involved, as you indicated, was some of the burning of the insulation. Is that a correct point? That's what you said. And the question then, the gentleman, if I may, is it the same type of insulation that's used in the field O-joint connection as is the same kind of insulation that's used in those joints that are factory sealed? Is that fair commentary, the gentleman from California?
Yes.
That's what we're trying to find out.
If you give us just a minute and let us get the view
Please,
graph.
and then let me pursue with
Be
my
able to-
questions and then come back, if I may. The thrust of my question, or the end result, is to find out if we're having a different history with the factory joints than we are the field joints. I think we are. Is that correct? Obviously, we're not showing a problem with the factory joints. Two questions that I would like answered. One, very simple. If we see no real problem and have no real history of problems with the factory joints, will they be included in any redesign? Will it be necessary to redesign those along with the field joints?
The answer is yes.
I know that's all being looked at, but let's get John Thomas to answer that. He's heading up the redesign team.
It's always better to get short answers.
First, to clarify the configuration. The field joint from here outboard looks identical. From here inboard, the insulation comes right down this way. The edge of the insulation comes right down this way and back against the case, and all this area here is then filled with propellant. So there is no gap in the insulation at this joint. It's a continuous path of insulation over the joint.
Let me pursue it a little bit then. The rotation has proven to be one of the problems under cold weather conditions. relating to the accident, do we find the same rotation problems at the factory joints as we do at the field joints?
Yes, sir. It just to a little bit lesser degree because of the influence of the continuous insulation across the skin, but it is, for all intents and purposes, the same.
And do field joints have the same, are they subject to the same problems of the cold weather as the field joints?
Yes, sir, they are.
And so they could fail under certain a set of circumstances similar to what we found failure here in this accident?
It is conceivable that they could fail under that set of circumstances. However, the joint is susceptible to the same degree of hazard as is the case about 6 inches away from it. And that is that if the insulation burns through or for some reason is fractured to the case, even at the point where there is not a joint, you would have erosion of the metal and weakening of the metal and a failure just as you would a joint. So in this case where you have insulation over it, it is essentially a continuation of the membrane.
Well, certainly we know that, or we've seen no breakdown or no evidence of failure of other joints other than the one that ultimately has been identified as the cause of this accident. I'm intrigued by the fact that all of the problems in combination that caused this accident, or the accident causing joint, and those that that contributed to the cause of the accident all fell into one specific area. I'd like to know if that's by chance, by coincidence, or whether in fact that is predictable and was predictable. We're looking now at about the 307 degree point on the field joint in the rear right booster. It was the coldest spot on that booster at that particular time of day when the launch took place. It was it had the most stress because it was next to the strut, and also because it happened to be the point of the maximum O-ring squeeze. All of that came at the same point, or essentially the same general area on that joint. Is that simply coincidental? Or in the shipping of it, where it goes out of round, do they ship that section, that particular section of the SRB, in the same configuration so that every section for every flight would be out of round and put the same kind of squeeze pressure on that, around that same strut, that 307 degree area?
The cases are shipped all are shipped in the same orientation. That is, with the 90 degree or tunnel position up on the rail car. So they're all shipped in that configuration. So that every out of round correction would be
would put the stress or the maximum O-ring squeeze at the same point, flight after flight.
I would say not precisely at the same point, but on that side of the vehicle.
So that it wasn't coincident that all things seemed to zero in to that one specific area.
I think excuse me, sir.
It's certainly wasn't designed that way, but that's the way it happens to be. Okay. I'd like to pursue, if I may, Mr. Chairman, just briefly this whole question of cannibalism and the extra workload that and we can turn the lights on if we like.
It is alarming that 45 parts out of 300 had to be cannibalized from another shuttle or another piece of equipment. That has to mean that there was a significant amount of cannibalism on from flight L-51 to the previous flight, which I think our gentleman from Florida was on. Was that true?
Yes, sir.
I have to assume that the very process of the human process of removing from one and putting it onto another simply geometrically increases the potential for error, for problems. Is that correct?
That's correct, sir.
It not only increases the possibility of error, but it certainly contributes substantially in this case, where we became almost a graduating process of increasing the workload of the people. As we increased the amount of cannibalism, the amount of change from one flight to another to get the flight off on schedule, that became, and that was exacerbated by increasing the flight schedule from what was initially planned to be 16 and then up to 24 or over a process. That must have put incredible pressure on the crew, or not the crew of the flight, but on the personnel involved in making these changes. Is that correct?
It was one of the frustrations of that did get to our launch team.
It came back to this committee long before the accident that this was becoming a problem, that we were overworking possibly the personnel. That, in addition, could create enough of a problem for where, well, when people are overworked, sometimes things can be overlooked. Is that because we have not had adequate spare parts in inventory?
The reason you cannibalize is because you don't have a spare part to draw from the shelf.
And not having adequate spare parts, did we find that in this particular case that we had to remove from other pieces of equipment parts that are now in retrospect attributable to the accident, the O-ring joint and any of that area?
No, sir.
No.
All those attributed to the joints are expendable parts.
I would assume that. So what parts generally are cannibalized?
It's normally parts that are high value, critical parts on the orbiter. And the common thread normally runs is there's been some problem where that they are in a repair cycle, or the repair rate may have been a little slightly higher than anticipated.
What effect will that have, or would that have had, on the Galileo and Ulysses missions that were scheduled to fly in May, this past May? Would that have reached a point? It was a progressive point and getting worse and worse as far as the cannibalism and also the extra workload that was creating. Would that have created a possible delay in those two flights, which had a very narrow window?
Obviously, the answer to that is a speculation. My own personal feeling is it would have created large frustrations with the workforce. I think that it would have forced us to look at priorities and workarounds, but my own personal belief, we would have found workarounds, but it certainly would have been a higher work factor and a frustration factor.
Be happy to yield.
For the record, why, just 2 points, why don't we have enough spare parts? Is it inadequacy in funding by Congress, or has there been some other decision process that gets in the way there? For the record.
I'd like to start, Mr. Chairman, with that, because I have had a chance to look into that both in my former capacity and more recently. We have to recall that this is really an R&D program. Sometimes we call it an operational system, but it's really an R&D system. And for R&D systems, you don't really have enough data to go on to get adequate spare parts. Also, you only had 4 orbiters, and the spare parts problem in that kind of a system is a lot different, say, for a 100 aircraft fleet, where the spare, especially a mature fleet, where you've had some experience on spare parts. I don't want to say that we couldn't have done better, because I'm sure we could have, but spare parts is not a trivial issue on any kind of an R&D program of this sort. Now, having said that, I'm sure there's experts that are closer to it than I am.
Well, I think what I'm really trying to get at, the gentleman yield further, well, just for the record purposes, has Congress not provided adequate funding to provide the resources for spare parts, or has part of the decision been made, for whatever the reason be, on NASA's part? Is there enough
To the best of
funding?
my recollection, since that has come up before, Congress has provided adequate funds for spare parts. Whatever actions were taken to reduce the number of spare parts, if it were done, was done within NASA.
Mr. Chairman, may I elucidate you further on that subject?
Gentleman from California will yield. Yes, of course.
Indeed, what Dr. Fletcher says is accurate. A case in point is last year. There has been a diversion of some of the funds that were authorized for spare parts by this committee. The specifics of that we can provide through documentation. This committee has come forth recognizing continually that spare parts is a problem and going to continue to be, and yet there was an administrative decision within NASA last year as a case in point that diverted some of the funds.
Let me just...
The gentleman from California, of course.
Pursue that just for one further question. If the policy decision is made, or if budget constraints force that decision, that there would we would live with three orbiters, and cannibalism continued at the levels that they've been in the past, what kind of problems would that create for us in keeping any kind of a schedule of what we're talking about now, 17 flights per year?
It would have created a large problem. We did look at it. Some of our people feel that we would have not been able to meet the schedule. The key to it would have been to be able to generate a rapid turnaround response on repairs with the various vendors in order to compensate for things not on the shelf. We were working to be able to do that, and that was our only hope of being able to meet the schedule. Would have been extraordinary efforts in the repair cycle.
Certainly that's going to be a decision that this committee is going to have to grapple with in the future, as to how we deal with the spare parts problem, the cannibalism problem, and the additional work that puts on to the personnel that get these off of the ground.
Well, gentlemen, yield at that
I would
point.
be happy to.
I know that both the gentleman from California and the gentleman from Florida are going to generate another series of questions, but I just want to, if I can intrude on that dialogue, the one thing I'm thinking about is the relationship of reusable parts as it relates to spare parts, as it relates to testing, which they're going to get into next. I think that becomes very important because of metal fatigue and so forth and so on. I don't know whether you want to start that or whether
Let me just ask two short questions before we get into that, Mr. Chairman. I'm interested in the putty as it because it's a part of this failed joint, and I want to make certain that there's not any portion of that joint that we leave unattended in this hearing. The putty is placed in Utah, Brigham City, Utah. It is much colder there. It is much different climate, different atmosphere, and altitude and so forth. In your review and any tests or research found that the putty acts differently at the factory there in Utah compared to at the Cape?
Yes, sir. The putty will react differently at differing temperatures. It will become more dense than at cooler temperatures and lower humidity than it does at warmer temperatures and higher humidity.
Now, is the testing generally done in Utah on that joint?
Yes, it is.
So the putty is tested in Utah.
Right.
Has there been any efforts to test the putty and its function, and the way it functions, whether it meets the
the design specs at the Cape?
Yes, we have taken during the investigation, taken the putty and conditioned it to the conditions that one would expect at KSC and the conditions that one expects at Brigham City, Utah, and tested those and compared the results. We're using 80% relative humidity at 75 degrees and 10 hours for the conditioning of quote, KSC putty, and slightly less than that for Utah putty. We have not been, however, able to create or produce enough tests to create a trend that one is significantly worse than the other.
Well, at the factory, in your factory joints, obviously the putty has remained much more, the integrity of that joint and the putty has been much more successful than it has at the field joints where they have to put the putty in there at the Cape.
Mr. Packard,
your tests have not shown where there has been any, well, maybe I've misunderstood that process, and I need to
there's no putty in the factory joints.
There is not.
There is
Well,
not.
Gentlemen, yield for a minute. I think it might be helpful to your question on the putty and help the committee in the following way, if I may. There's some dialogue going around that as the gentleman from California is pointing out, in reference to the putty issue itself per se, that originally, purportedly, NASA used one particular manufacturer of a particular type of putty, which used asbestos as part of the base, as I understand it. That company purportedly went out of business or wasn't going to make the putty anymore, and another company was selected to do that, and there was a question as to whether or not the same formula of the same was identical in the same putty issue. Could you give us, the gentleman from California, because I think it's important to get it here in the record, could you give us just a little background and a rundown on the putty issue? Because I think that bears upon what the gentleman is speaking to from California.
Yes, sir.
What factually happened there?
Your scenario that you just stated is correct in that the original supplier of the putty, which was I'm trying to recall the trade name for it. Anyway, it was an asbestos field vacuum putty that was of Fuller O'Brien, I believe is the name of it. They went out of, or they stopped making putty, and the putty that the new vendor for the putty, although it is asbestos filled as was the other, it is made by Randolph, and it has essentially the same consistency. It reacts a little bit more to humidity, that is, it gets a little less dense or a little bit less viscous with higher humidities, but it essentially serves the same purpose.
And to finalize this point. Yes.
Gentleman from California.
Be happy to.
I would like to know, were any viscosity tests ever run on the putty at higher temperatures at the interior of the SRB during firing?
We have run viscosity at levels of putty at varying temperatures, but I don't believe we ran it up that high.
I mean, the putty is subject to those temperatures when the SRB is being fired, is it not?
It initially at the very end of the putty path between the two motors, initially there is the high heat rate. It will erode back with the propellant as it comes back toward the joint, but at the time that the propellant stops burning and then progresses up the bore, it becomes relatively cool.
Well, you still didn't answer my question. Is the putty subject to that temperature of the inside while the SRB is being fired?
It is subjected to that temperature.
I know it's for a relatively maybe short period of time, but it's up to that temperature.
Yes, sir.
And we don't know what the viscosity of it is
Well, I think
at those temperatures.
At those elevated temperatures, I believe the putty just chars along with the propellant as it goes back.
It chars.
Yes, sir.
Do you know if it
Chars.
gets real runny, almost like, say, real soft butter or anything like that?
No, sir, we don't believe it does, because it stays a relatively cool temperature about a short distance from the burning surface, because it's dissipating its heat back into the insulation. I can provide that.
Let me
for the
reclaim my
record.
time and just ask a question and conclude this item on the putty. Were any tests run on the putty before the accident?
Yes, sir, there were a series of tests run at the time this transition took place from the Fuller O'Brien to the Randolph putty.
And do we know the difference between the reaction of the putty when it's being tested in the horizontal in Utah versus how it reacts at the launch pad?
I think I can't say that we've tested that specifically in the large motor. We have tested it in a small motor during the investigation, although we have in the static motor test at Utah, the putty has been examined from the inside to determine its characteristics. It has been repaired a number of times prior to test, and from that standpoint, we understand its characteristics.
My perception is that perhaps NASA would do well to be more familiar with the actual formula for putty and how it operates. We may be leaving that to the manufacturers and to the contractors in preference to, without us being fully familiar, and I can understand that because we're certainly not. One last question, Mr. Chairman. It's bothered me for the last 2 days. In fact, since we were down there and I saw the pictures of the launch pad. Now, for the first time today, I came to realize that Pad B was used for the first time with L-51. I wasn't aware of that, and for that means then that the failure of the freeze plan happened on the very first usage of the pad, and the water system. Would you have launched, the decision makers for go or no go, would you have launched had the rains fallen and created the amount of ice both in the joint and on the pad to the same extent that the failure of the sprinkling system created? Would a decision to have launched had you had rain that would have caused those same kind of icicles and the same kind of water problems and ice problems in the joint as the sprinkling system did? That's a hypothetical question, but I think it's interesting.
Well, I guess from the viewpoint, the analysis on, let's take the ice on the fixed service structure and that, I think the analysis would have indicated, because the source of the icicles would have been the same, and so from that basis, I think the decision would have been the same from that aspect. As far as water in the joint, we did not know of the phenomena of water in the joint until after, as part of the investigation, and so I'm not sure what we would have done in that case. There may have been many other factors, though, on a cold night and raining like that would have much precluded that.
Well, I think you've seen the picture, of course, that we've seen in the report, and as you look at it, it becomes incredible that we would feel inclined to launch with that kind of environment. In our briefing on Friday at the Cape, one obvious way to prevent water and thus ice into the joint, which I think the Commission's report certainly indicates had a profound effect upon the resiliency of those O-rings. In fact, the report says that perhaps maybe not contrary to Admiral Truly's comment that the cold weather was had more adverse effect than the ice and the water did. But at any rate, this report says that the ice did displace the O-rings, that it actually displaced them, which had an effect upon the ultimate seal. Simply turning that joint over, reversing it so that it does not point upward, thus water and ice flowing down into that joint, would appear to be a simple way, although probably a costly way now to redesign. But certainly, it is an open trough that clevis points upward that allows the water to flow right down around the tang fitting into the clevis. But we're not in the redesign business. But certainly that ice can be easily and water can easily be prevented from entering into there.
Mr. Packard, you're exactly right. I think that probably at this stage would be a very costly fix, but I can assure you that the redesign fix will not allow water into that joint.
That's fine. Mr. Chairman, I'll yield back my time.
One of our colleagues suggested to the distinguished gentleman from California, he praise be the Lord, to see a spaceship designed by the Congress. The chair recognizes the distinguished lady from Tennessee.
Thank the chairman. Mr. Chairman, we've been talking about safety and throughout our hearings. I really think another thing we might revisit is how well we do manage risk, because certainly this determination has to be made on every flight. The Washington Post had a very descriptive diagram, if you didn't see it, an article the 25th of May that really gives us a very succinct description of the steps that are used to determine your risk management program. I'd like for Dr. Fletcher, or if you would, or someone else, if you might like to refer to someone else, to describe the elements of NASA's risk management activities, is what really supports your risk management decisions.
Well, I will start, Mrs. Lloyd, but risk management is a pretty generic term. Risk management is decided in headquarters in terms of what are the chances of a overall failure of the system and under a given set of circumstances. When you get down to the flight team, the launch crew, those last several hours or a couple of days, risk management is an entirely different thing. They have to look at the factors that have come up just before launch and assess whether this is a risk we want to take. This is a judgment question. You can't make calculations
well, I
at this
realize
point.
that on the day of a launch that that might be the case, but Dr. Fletcher, I do think there are procedures and methods that are used to assess risk. I think Dr. Silvera testified before my subcommittee with, as well as Mr. Nelson's, at a joint hearing last March on this subject. And if you'd like to, if you'd like me to speak to Dr. Silvera to address this question, him would be fine with me.
Yeah, I guess.
As we had mentioned in the testimony that we had given previously to yourself and Mr. Nelson, the only time that we had gone into trying to assess a probability, if you will, a risk, was as the result of a request that was made by DOE for their analysis that they were performing at that time to assess the probability of failure of the vehicle, to assess the danger when we're flying the RTGs, the radioactive material. As far as in our program and any major decisions that we would make, we have a number of reasons why our past history had indicated that was not a good way of doing it. As a result, we don't use it generally in our risk management. We prefer using things like the failure effects and analysis that we do, the technical engineering judgment, using things like the SIL to supposedly control our failures rather than depending on a probability analysis to assess it.
But basically, what do you do beyond the failure mode and effect analysis, Dr.
Well,
Silvera?
Yes, ma'am. Any time that, of course, we do have a failure component, and we track these very carefully from our ground test program as well as our flight test program, we go back and make sure we thoroughly understand that failure, and of course affect a redesign to ensure that failure will not repeat
You would
itself.
test the components at that point.
Yes, ma'am.
All right. Dr. Silvera, what was the basis for NASA's assigning a probability of 1 in 100,000 to a catastrophic SRB failure?
Well, as I say, as a result of a request from DOE to assess a number, we went back and attempted to look at various parts of the vehicle, various systems to establish a probability of failure of those particular components. When that was added to a statistical analysis, and indeed a lot of these things don't lend themselves to a statistical analysis. For instance, as I say, every time you have a failure, you repair it, so you destroy your database, and you really don't have a good database to go against. So as a result of trying to come up with these numbers for the use in the safety analysis, our people developed numbers, went back and combined them, and then came out with a number that said that it would be more like 10 to the minus 5 in our analysis, 1 in 100,000 cases. Now, there are verbs that were in the shuttle data book that was the official transmission of that data, which I think that we had provided the staff earlier to look at, that said that indeed that was a case where a failure would be highly unlikely, that it was remote to happen.
If you remember,
and in some of the redundancy that we provided and increased safety factors that we provided in our design, and as a result, we felt that study was not proper. Since that time, the Air Force has conducted additional studies with the Wiggins group, that's now another group, plus Sandia and other people, to try to assess what they would figure, using, again, the statistical database from previous experience with solid motors, and come up with a number that they had. When where we left the study, their statistical numbers would come out like about 1 in 100. They said, we think
reference was made to the report by Teledyne and Sandia and the Wiggins Company.
Yes, ma'am.
And this claimed the probability number would be somewhere between 1 in 34 to 1 in 10,000. So I just wanted you to explain this discrepancy for the record, Dr. Silvera.
Yes, ma'am. As you recall, back in about the 77 time period, NASA had commissioned the Wiggins group to go and perform a study for range safety purposes. Now, at that time, we weren't looking at the vehicle with a Centaur vehicle on board and alike. And their analysis went back and looked at all the statistical data of all vehicles at that time and said that the probability of failure is like 1 in 57 in that order. Of course, we said that's like comparing apples, oranges, and things like that. There are a lot of vehicles in that family that don't relate to our vehicle. We think we're somewhat unique in the way both that we operate and in some of the redundancy that we provided and increased safety factors that we provided in our design, and as a result, we felt that study was not proper. Since that time, the Air Force has conducted additional studies with the Wiggins group, that's now another group, plus Sandia and other people, to try to assess what they would figure, using, again, the statistical database from previous experience with solid motors, and come up with a number that they had. When we, where we left the study, their statistical numbers would come out like about 1 in 100. They said, we think it's really better that for the reasons that more conservatism in the design and alike. Said it would be about 1 in 1,000. We said we still adhere to our number because we think a failure is highly improbable in the shuttle. We agreed that we would plug in the range of numbers, their 1 in 1,000, our 1 in 100,000, see how that would affect the end numbers as far as the safety as far as flying the radioactive material. And that was about the place we were headed at that time.
Well, do you intend to revisit this decision? So I certainly think we should make the very best risk management analysis that we could.
Yes, ma'am. Of course, we're going back and looking particularly at the Challenger tragedy to look at yields, how the vehicle failed. As you recall, another big discussion that we were having with the people that were reviewing us was the matter of how the vehicle broke up and the forward bulkhead analysis.
Are you looking at a statistical database? It might really help you in your analysis.
I think, of course, we will go back and look at whether there's anything else that we can pull out there. But, of course, we will still have a hard time in changing our statistical database from anything we know as far as the Challenger is concerned right now.
Well, could you establish a database?
As far as a probability of occurrence?
That's right. Mm-hmm.
I think we would still have a hard time doing that and saying that we were going to use it for any management decision.
Well, it would be an expensive
Well,
proposition.
if you mean go back and do testing on a thing, you know,
Yes, that's what I mean.
As we had in the shuttle data handbook, that if we performed a certain function 1,000 times, the only thing that we would, and did it successfully, tested 1,000 times successfully, that would only give us a confidence factor of we would possibly have 3 failures in the next 1,000 events with a 95% confidence factor. So we don't think that we could do that much testing. Of course, as soon as we saw any anomaly in that testing, we would go back, redesign, try to fix it, and then you'd have to reestablish your database and start testing again.
Well, it didn't work for the Challenger, and I feel that this is an area where we need to really revisit and
Yes, ma'am.
look at again. Thank you very much. Thank you, Mr. Chairman.
I thank the gentlelady from Tennessee. The gentleman from Pennsylvania, Mr. Walker.
Thank you, Mr. Chairman. Let me say, first of all, I admire the stamina of all of you sitting there and so on for all this time and so on. You've done a remarkable job of testifying and so on, but you've also shown great stamina. Let me ask just a couple of questions about whether or not you now see, as a result of the investigations done by your technical people, and also as a result of the Commission report, whether you now see changes in what you are going to do in flight rules. May not be the best term, and that may not be a precise term, but I'm thinking about you obviously are not going to fly in low temperatures now. You now know that very low temperatures are probably a reason not to fly on a particular day. There were other things that caused you not to fly in the past. If you had wet weather, for instance, we didn't fly because of the possible problem with the tiles. Have you now developed another set of things growing out of the Challenger incident that will give you new points of departure each time that you fly, things that you will decide not to fly?
We, as a result of the accident, and one of the things that I directed be done was a complete reassessment of mission rules in the launch and abort mission phases, and the Mission Operations Directorate at Houston has taken that chore. Frankly, in the things that we're doing, number one, they're not through. they're not finished that. And if any specific mission rule changes have been made to this point, I'm not aware of them, but I intend to review their work. On your point about cold weather, I think there's certainly going to be an emotional reason not to launch in cold weather. I would put it a different way. We're going to make sure that whatever weather we launch in, be it temperature or environment or clouds, is one that we're totally confident that we have certified and tested to, and that there is no doubt in anybody's mind, be it whether it be a level 4, 3, 2, or 1, that we're ready to launch, no matter what the temperature is.
Would it be helpful if this committee were to help you get a Doppler radar at the Cape for better local forecasting?
Don't kick this horse in the face.
I wish I was the one that is doing that weather analysis. Could I get Mr. Aldrich to come to the to the microphone if he's here and answer that question and tell you where we are on our attempt to upgrade weather forecasting capability?
Mr. Walker, we've been discussing Doppler radar systems for better real-time understanding of the upper-level winds for some time. And as I answered Mr. Nelson's question yesterday, we have a intent to pursue those systems for direct application for that use. My understanding so far is that it will be even more useful for the kind of upper-level winds we regularly see at Vandenberg than for Florida, and we have approved recently with the Air Force a test program of a Doppler radar there. We're very encouraged that these will add to our capability, and certainly we would be appreciative of support in providing these systems as we can understand what they'll contribute to our overall system.
As I understand it, they would at least provide us with a better handle on wind shear. Is that correct?
We need to test to be sure we understand what they will tell us, and it's very promising and hopeful that they will. Yes, sir.
And when I talk about flight rules, the one thing that concerns me, having viewed your timeline, and I've raised a question briefly this morning on it, is that it appears as though the launch of 51L, that at the time the maximum dynamics were on the craft, it was also a period of time when it was experiencing a wind shear problem, fairly strong wind shear problem. Will we be reviewing a pattern of not launching if we have reason to believe that we have significant wind shear at altitudes where the ship would be undergoing its most massive loads?
Can I answer that, Dick?
As you know, we've always had launch rules which depend on wind shear at altitudes. What we're talking about with the Doppler radar is having a better fix on that wind shear. We mostly have estimated wind shear from the magnitude of the winds and so forth, and estimated the wind shear. Measurement precisely, of course, will be improved somewhat by the Doppler radar, and I imagine that's what we're talking about. We have to really test to see how much better that is before we implement a Doppler radar system.
Well, I really do think that the wind shear question becomes an important one, at least in my mind. For example, have you correlated the winds aloft on 51C with the winds aloft on 51L? Since 51C was where I understand we also had a fairly significant O-ring problem. Has that as a contributory problem been correlated at this point?
Yes, sir, we have correlated not specifically, I don't recall whether we did 51C or not, but we looked backwards to see if we could see any correlation that would show that this one was worse than any of the the previous flights, and we selected the previous flight the worst previous flight to compare, and unfortunately I don't remember which one that was, whether it was 51C or not. but we did go back and look at.
Okay, now,
the-
when you went back and looked, did you find that on the two flights, you had a fairly similar wind shear problem at the time that the load design on the ship was the greatest?
I don't recall that, Mr. Walker, I'm sorry. Whether we did that or not, I would have to review the data. I just don't recall that
Okay, I would
offhand.
appreciate if you would letting us know on that and getting back to us, because it seems to me that that the fact that you had the initial failure that we see in the black puff of smoke, then the resealing, and then the understanding now that at the point that the ship was under the greatest dynamic stress loads, that it then failed a second time, or the failure became catastrophic, that it may well be that the winds also contributed to that particular problem, and it would be, I think, very advantageous to know whether or not there's a correlation then to past failures, because it would certainly play a role in it seems to me, some design decisions if we're finding that the buffeting of that ship by winds has a role to play, and it certainly would seem to me that that then becomes a question on launch rules. Does all seem logical?
Mr. Aldrich would like to add a comment to that. He is very familiar with what happened on 51L with the wind shears, and I think it would help you resolve this issue.
All these conditions we've discussed with 51L were the result of a major cold front that came down from the central part of the country across Florida, and the conditions on launch day with the temperatures and the final winds at the back of that front. The system we use have used currently, involve balloon launches and some very elaborate calculations to try to predict the winds based on the conditions we know and see. And I think your point is well made that there were some unique weather-related shear conditions here potentially that could not be predicted through those approaches, and we are certainly reviewing that, both in terms of other indicators that we might have had that would be in addition to the Doppler weather, and in terms of changes or more conservatism in the rules for those kinds of weather patterns. And I think, yes, all of those points are well made, and we are and we'll be looking at those.
So that what you'll end up doing is establishing some different weather parameters for the launch director to use in making his decision, and they will be more conservative than those that you've used in the past.
We will be looking at doing that, yes. I understand the weather community now assesses the general conditions to indicate a higher potential for shear than we were, in fact, dealing with our balloons and our calculations on that day. And you can't prove what was there at the exact time of the launch, but you can postulate that shears could have been more prevalent or more significant than was expected.
Thank you, Chair.
Thank you, gentleman from Pennsylvania. The gentleman from Missouri, Mr. Volkman.
Thank you very much, Mr. Chairman. I have several areas. First is a technical one. Can you tell me how it's possible to maintain a tolerance of plus 5 thousandths and minus 3 thousandths inch on a piece of rubber roughly 1/4 inch in diameter, is 37 feet long?
The process is that the O-ring is formed and then it is ground with precision instruments to that diameter. It is actually ground that way.
All right, now, at what temperature is it ground?
Ambient temperature.
In the plant or factory, wherever it's done?
Yes, sir.
And that could be 75 degrees or 80 degrees or 60 degrees, somewhere in that area. I'm sure they don't work it too cold. And we do know, as I asked down at Kennedy, we do have some loss in coldness, do we not?
Yes, sir, we do.
And doesn't that then affect the amount of tolerance?
It on the when we compute the squeeze, computed the squeeze numbers on 51L, we took into account the differential coefficient of expansion of the rubber down to the lower temperature, and as I recall, that amounted to approximately 0.03 of an inch on the diameter.
All right. Now, that's 0.03 additional.
3,000 smaller in diameter.
It's 3,000 smaller than it was in the factory.
Yes.
Now, if it's already down 0.03 because of the tolerances permitted, then you're 0.03 under, are you not?
When we compute squeeze on the O-ring, we use the minimum specification diameter, which is the 0.03 less, or a 0.277 O-ring. So it would be 0.03 below the 0.277.
But if it came out of the factory with a 0.03 less?
We assume that it does that under any case. We assume in computing squeeze that it is of a minimum diameter.
All right. But what I'm trying to get at, then the cold also reduces it to 0.03
by 3,000.
In addition.
Yes, sir.
So now you're actually under the specifications, the tolerance level.
The maybe I should explain that the minimum O-ring squeeze is 7.5% of the diameter, and in order to assure that we have that, we take all of the worst-case dimensions for the as-machined configuration of the metal and the minimum specification number for the O-ring, and then be sure that the shim that is installed into the clevis produces more squeeze on the O-ring than the minimum. And in 51L, we still met the minimum squeeze condition with the 0.277 presumed O-ring and the 0.03 shrinkage due to temperature.
All right. Continue on with the O-ring. On page 158 of the Presidential Commission report, there is a document known as SRB Critical Items List. On this, it says a more detailed description of SRM joint testing history is contained in TWR-13520 Revision A. Have you all reviewed that? That testing history?
I'm sorry, sir, I don't recall which one that is. That is, I believe, is attached to the critical item list revision of about a year ago.
That'll be
I don't recall.
More than a year ago, because this document's dated December 17, 1982. So it has to be prior to 82. I'd like for you to furnish us a copy of that document.
Yes, sir.
Specifically, I'd like to have a copy
We
of
will
that
do
document.
so, Mr. Volkman.
I know we have a vote going on. I have several more questions. To get into the question of temperature, what is more important, ambient or air temperature, or the temperature at the joint?
Temperature at the joint.
Then why don't we, when we make a determination of whether we meet criteria in order to launch, require a certain temperature at the joint?
That should have been a mission rule.
It should be in the future.
Yes, sir.
Now, earlier we had testimony yesterday about the 31 degrees Fahrenheit temperature for the SRB itself. That only related to, as I understand it, to the total SRB, or the ambient temperature at the time of the launch. Is that correct?
Let me ask Mr. Lee to respond to that. I'm not aware of it.
That is the natural environment, outside temperature, if you will, the 31 to 99 degrees. That's right.
Right. That's the. So yesterday when the I asked a question of what the temperature was at time of launch. That was 36 degrees. That's the outside temperature also.
Yes, sir.
That does not relate necessarily to the temperature of any part of the SRB, including the joints.
That's true.
And I guess we found out it's more important to worry about the temperature of the SRB and joint temperature and other things. Is it not correct?
Absolutely.
Temperature at other points.
Absolutely.
Now, I'd like to ask anyone who wants to answer this question, if you want to do so. Does
Would the gentleman yield? Is the gentleman planning on voting?
Oh, I'd like to.
Well, we're on the second call. Why don't you and I vote and come back again?
Okay, fine.
Why don't we suspend for about 10 minutes? We'll be right. We should finish up in about 20 minutes. The committee will convene only for a short period. We've just learned that there'll be at least 2 to 3 more votes, and they're imminent. And I've talked to Mr. Nelson and Mr. Volkmer, and we agreed that we do have some additional questions, but we will put those in writing and forward them to you. And should there be an occasion that we think we need additional personal testimony, then we'll be back in touch with you to see what we can work out. In the meantime, I want to, on behalf of the committee, and I know you have an observation you'd like to make, Dr. Fletcher, so if you would proceed, please.
Mr. Chairman, I'd like for the record to personally express our sincere thanks from all of NASA to the Princeton University for making J.R. Thompson available to the task force for these past months. I recognize the importance of his position at Princeton, and I'm sure his availability to us was not without significant impact to his work at Princeton. As you know, he's Deputy Director of the Tokamak program down there. Sure. NASA and the nation should be grateful. And I might add, I appreciate your forbearance, Mr. Chairman, for all of us in answering your questions.
Well, I appreciate that. And on behalf of myself and the committee, I want to thank you, Dr. Fletcher, and Admiral Truly, and Dr. Thompson, and all of the other distinguished representatives of NASA that have testified over the last 2 days. I think your contribution to the record and your contribution, education, to educating the members of the committee and providing the substantive information in candor and right up front is what was necessary at this point of our proceedings. So we want to thank you for your patience, your forbearance, and your indulgence. It's been very productive. Now, for the benefit of the other members that are here or their staff people, we will now, in effect, adjourn today, but we'll reconvene. The word has left me. We'll reconvene on Tuesday at 9:30, and our first witnesses up will be Thiokol, and then we're going to have, in the afternoon, the representatives from your Marshall Space Station. So there's what our schedule is down the road. Again, many thanks. We appreciate it. The hearing stands adjourned.